Some stars are older than the Milky Way itself. It's a statement that feels impossible at first. After all, we tend to think of our galaxy as a kind of ultimate cosmic container, a vast home to hundreds of billions of stars, planets, and clouds of dust and gas. The Milky Way feels ancient beyond comprehension, a colossal spiral that has existed forever in the darkness of space. But this is an illusion born of our limited human timescale. In reality, there are stars scattered throughout our galaxy's outer reaches that predate the Milky Way entirely. They are survivors from an era before our galactic home even existed, ancient suns forged in the raw, unshaped universe just after the Big Bang, still burning quietly today. But before we continue, subscribe to the channel so you don't miss out on any of these videos. To grasp the significance of that, imagine time not as numbers on a clock, but as an unfathomable ocean stretching back 13.8 billion years. Our Sun, bright and life-giving, emerged just 4.6 billion years ago, meaning it has lived for barely a third of the universe's history. By contrast, some of these older stars, called halo stars, began shining when the cosmos was still shrouded in primordial darkness. They are like flickering lanterns left behind by a civilization long gone, except in this case, this civilization is the first generation of stellar activity in the universe. The idea of these stars existing at all is deeply humbling. Picture the early universe. There were no galaxies yet, no great spirals like the Milky Way, no planets, no life. Space was filled with a thin fog of hydrogen and helium gas left over from the Big Bang, cooling and condensing into the very first pockets of light. These first suns ignited, burned brightly, and in some cases, died spectacularly in supernova explosions. But some, particularly the smaller, slower-burning ones, endured. They survived the violent mergers of young galaxies, the gravitational chaos of the cosmic web forming, and the birth of new galactic structures. They wandered the universe long before the spiral arms of our home took shape. What's perhaps most extraordinary is that they still exist now, orbiting far above and below the Milky Way's familiar disk, tracing lonely paths through the galaxy's halo. Every photon of light from these stars is a direct messenger from the universe's youth, carrying in its spectrum the chemical story of an era when heavy elements were scarce and the cosmos was still in its infancy. The fact that we can see them at all is a kind of cosmic miracle. The vast majority of the stars born in those first billion years of the universe have long since perished. The earliest, most massive stars burned themselves out in just a few million years. But a tiny fraction, the low-mass, long-lived stars, have lifespans so vast that they can survive for the entire age of the universe, perhaps even longer than the universe's future projected lifetime. These are the ones we encounter today as halo stars, quiet, dim compared to our Sun, but carrying with them the fingerprints of the ancient universe. And here's the part that really tilts your sense of scale. The light from our Sun will fade billions of years from now. The planets will be gone, Earth will be a memory. The Milky Way itself may have merged with Andromeda and transformed into some new galactic form. And yet, some of these halo stars will still be burning, perhaps even wandering in intergalactic space, outlasting the very structure of the galaxy that currently hosts them. It's no exaggeration to say that halo stars are living fossils. They are not just remnants of cosmic history, they are cosmic history. When you look at one through a telescope, you are staring at something that began before the familiar sky even existed, before there was a Milky Way to place it in. This is why astronomers speak about these stars with such reverence. In their orbits, in their chemical signatures, and in their very existence, halo stars preserve a record of a time so remote it's almost alien to human comprehension. They are suns from the dawn of time, witnesses to the unfolding of the universe itself. When astronomers talk about halo stars, they're referring to a very specific and somewhat mysterious population of stars, the loners of our galaxy. These are not the bright, showy residents of the Milky Way's spiral arms, where most of the galaxy's stellar drama unfolds. They don't participate in the dense, bustling neighborhoods of star formation where massive clouds of gas are constantly giving birth to new suns. Instead, halo stars live far away from the crowded galactic disk, in a vast, ghostly sphere of space surrounding the Milky Way that we call the galactic halo. Imagine the Milky Way as a glowing, flat disk, like a giant, cosmic frisbee, brimming with billions of stars, dust lanes, and spiral arms. Now picture a giant, nearly invisible bubble of space around it, extending far above and below the disk, wrapping the galaxy in a loose, spherical shell. This is the galactic halo, and the stars within it are like scattered fireflies in a vast dark field. They are few and far between, often separated by immense distances, drifting along quiet, solitary orbits that take them far from the galaxy's main hub of activity. Halo stars are ancient, and I mean truly ancient. They are some of the oldest surviving suns in the universe. Most of the stars we see in the Milky Way's disk today are relatively young, with ages measured in the hundreds of millions or a few billion years. Halo stars, by contrast, often clock in at over 12 billion years old. They were born when the universe itself was just a fraction of its current age, long before our galaxy's graceful spiral arms had even coalesced. Another defining trait is their movement. While disk stars like our Sun orbit the galactic center in neat, mostly circular paths, halo stars take much more chaotic, elongated routes. Their orbits can be tilted at any angle, plunging them far above the galactic plane and then sweeping them back down. These unusual paths are a clue to their origins. Many halo stars weren't born in the Milky Way at all. Instead, they likely formed in smaller, early galaxies that were later swallowed by the Milky Way in gravitational mergers. The stars from those ancient systems were flung into the halo, where they've remained ever since, like relics in a cosmic attic. Halo stars are also chemically distinct. They tend to have extremely low metallicity, which, in astronomy, means they contain very few elements heavier than helium. This is important because the very first stars formed from nearly pure hydrogen and helium left over from the Big Bang. Heavy elements like carbon, oxygen, and iron were forged later in the cores of stars and spread into space by supernova explosions. So, the fewer heavy elements a star has, the earlier it must have formed in cosmic history, before the universe had time to enrich itself with metals. Halo stars, with their ultra-low metallicity, are thus a kind of time capsule from the era of the first and second generations of stars. To put it simply, halo stars are ancient suns, often with strange orbits, low heavy element content, and locations far outside the galaxy's bustling main disk. They are survivors from a time when the Milky Way didn't yet exist in its current form, and their very presence is evidence that our galaxy has a long history of cannibalizing smaller systems and absorbing their stellar populations. In some ways, halo stars are the outsiders of the galactic family, the quiet elders who keep to themselves, far from the crowded neighborhoods, yet hold some of the most valuable stories about the galaxy's past. They don't draw much attention, but without them, our understanding of the Milky Way's formation and the early universe would be incomplete. Surrounding the familiar, bright disk of the Milky Way is something far larger, older, and more elusive, a structure so immense that if you could see it with the naked eye, it would make the galaxy look less like a tidy spiral and more like a glowing ember suspended inside a vast, transparent sphere. This is the galactic halo, and it's one of the most mysterious regions of our cosmic home. The halo is not a thin shell. It's an enormous, three-dimensional sphere of space that stretches hundreds of thousands of light-years in every direction from the galaxy's center. To give a sense of scale, the bright disk of the Milky Way, where the Sun, Earth, and most stars we know reside, is about 100,000 light-years across. But the halo extends several times farther, blending eventually into the intergalactic medium, the sparsely populated space between galaxies. It is the galaxy's outer frontier, where the gravitational pull of the Milky Way still dominates, but where the density of matter is extremely low. To the human eye, the halo is essentially invisible. It isn't lit up like the spiral arms, and it isn't filled with the glowing gas clouds we associate with star-forming regions. If you could magically place yourself in the middle of it, you wouldn't be surrounded by a dazzling field of lights. Instead, you'd see darkness broken only by the occasional, isolated star, perhaps a small cluster here or there, and the faint glow of the Milky Way's disk far in the distance. It's a region defined more by its emptiness than its content. Yet hidden within that emptiness are some of the most intriguing objects in the galaxy. Scattered throughout the halo are ancient stars, the halo stars themselves, and dense, spherical groupings of stars known as globular clusters. These clusters, some containing hundreds of thousands of stars packed tightly together, are also among the oldest structures in the Milky Way. Many of them formed over 12 billion years ago, making them nearly as ancient as the halo stars they accompany. But the halo is more than just stars and clusters. It's also home to vast amounts of invisible dark matter, an unseen substance that exerts gravitational influence but doesn't emit or reflect light. In fact, the dark matter in the halo outweighs the visible stars by a staggering margin. The halo's shape, density, and extent are largely determined by this dark matter, which acts as the galaxy's gravitational scaffolding. Without it, the Milky Way could not hold itself together. The rapid rotation of the disk would simply fling stars outward into space. The halo is not perfectly uniform. Astronomers have found that it contains streams of stars, long, thin trails that arc across the sky, which are the remains of smaller galaxies torn apart by the Milky Way's gravity. These stellar streams are like cosmic fingerprints, evidence of the galaxy's violent past and ongoing growth through mergers. Every stream, every lonely star, and every ancient cluster in the halo is a piece of a much larger puzzle about where our galaxy came from and how it evolved over billions of years. It's almost ironic. The halo is so faint and so empty that it's invisible to the casual observer, yet it is arguably the most important part of the Milky Way for understanding its history. If the spiral arms and the galactic center are the galaxy's present-day heart and soul, the halo is its ancient memory, stretching back to the dawn of cosmic time. It's here, in this vast and quiet realm, that some of the oldest relics of the universe continue their slow, eternal dance around the galaxy. One of the most remarkable things about halo stars is that, while they may look fairly unremarkable through a telescope, faint points of light adrift in the darkness, their true identity is revealed in the chemical code hidden in their light. Every star carries in its spectrum a signature of the elements it contains, a kind of stellar DNA. For astronomers, this is the key to determining a star's history, and in the case of halo stars, it tells us something extraordinary. Many of them were born when the universe was still in its infancy, at a time when the periodic table as we know it was almost empty. The story begins in the first few minutes after the Big Bang. During this brief period, known as Big Bang nucleosynthesis, the universe forged only the simplest elements, mostly hydrogen, a smaller amount of helium, and trace amounts of lithium. There were no heavier elements, no carbon, oxygen, iron, or gold. Those would have to be built later, deep inside the cores of stars, and then scattered into space by supernova explosions or other violent stellar deaths. When the very first stars formed, what astronomers call population 3 stars, they were born from this pristine cosmic material, containing virtually no elements heavier than lithium. They were massive, short-lived, and burned through their fuel in just a few million years before dying in spectacular explosions. These explosions seeded the universe with the first metals. In astronomical terms, anything heavier than helium is called a metal, enriching the gas from which the next generation of stars would form. Halo stars belong to this next wave of creation, what we call population 2 stars. They formed from material that had been touched only lightly by the first round of stellar enrichment, meaning they have incredibly low metallicity. In some cases, the amount of heavy elements in a halo star is thousands of times lower than in the Sun. To put that in perspective, our Sun's composition is about 98% hydrogen and helium, with the remaining 2% being heavier elements. A metal-poor halo star might have a heavy element content of less than 0.01%, so little that the lines representing metals in its spectrum are barely detectable. This lack of metals is more than just a curious statistic. It's a direct window into cosmic time. The low metallicity tells astronomers that these stars must have formed before the universe had a chance to produce many heavy elements. In other words, they were born when the cosmic chemical pantry was almost bare. This puts their birth date very close to the Big Bang, in an era astronomers refer to as the Cosmic Dawn, when the first galaxies were beginning to assemble. Some halo stars are so metal-poor that they may have formed just a few 100 million years after the universe began. These stars are living fossils, their light carrying the chemical fingerprints of the first supernova explosions. By analyzing the abundance of specific elements, such as carbon, magnesium, or iron, astronomers can even make educated guesses about what kind of population 3 stars seeded the gas clouds from which these halo stars were born. For instance, certain unusual ratios of elements suggest enrichment by a single massive supernova rather than multiple events. A perfect example of this is the halo star known as SMSS J031300.36, 670839.3, located in the halo of our own galaxy. This star has such an extraordinarily low iron content that it is effectively iron-free, making it one of the most chemically pristine stars ever discovered. Its composition suggests it formed from gas enriched by just one massive, first-generation star that exploded in a relatively weak supernova, producing very little iron. It's as close as we've come to finding a second-generation star, forged directly from the ashes of the very first stellar generation. The chemical makeup of halo stars also helps distinguish them from younger stars in the galactic disk. Disk stars, like the Sun, formed after billions of years of galactic recycling. Countless generations of stars had already lived, died, and seeded the galaxy with metals. That's why the Sun has a relatively high metallicity compared to halo stars. It was born into a galaxy already rich in elements, which is also why planets like Earth could exist at all. Heavy elements are the building blocks of rocky worlds. But halo stars formed before this enrichment process had fully unfolded. Many of them were born in small, primitive galaxies that merged into the Milky Way long ago, bringing their ancient, metal-poor populations with them. Because the gas in these early galaxies had only been enriched by 1 or 2 generations of stars, their stellar populations are chemically distinct. By studying these chemical signatures, astronomers can effectively tag a star as having originated in a particular ancient system, like tracing the ancestry of a fossil to a specific region in prehistory. What's truly astonishing is that the chemical trail in a halo star's spectrum has survived for over 12 billion years. Unlike living organisms, stars don't drastically change their surface composition over time, especially small, cool ones. That means a halo star's atmosphere still carries the elemental makeup it was born with, allowing astronomers today to read its ancient chemical story as if it were written yesterday. And so, in a way, halo stars are not just witnesses to the early universe. They are messengers, carrying in their light the unaltered memory of the first great bursts of creation after the Big Bang. Every low metallicity spectrum we observe is like finding a perfectly preserved relic from a vanished world, a tangible link to the time when the universe was young, raw, and brimming with potential. In their faint glow lies the record of a cosmos still learning how to make stars, planets, and the complex chemistry that would one day give rise to life itself. When astronomers talk about the ancient nature of halo stars, they often group them under a broader category known as population 2 stars. This is not just a casual label, it's part of a systematic way of classifying stars based on their chemical composition, age, and place in the cosmic timeline. Understanding this classification is like learning the language of stellar genealogy, and it reveals exactly why halo stars are recognized as some of the oldest suns in the universe. The system itself has a fascinating history. In the mid-20th century, astronomer Walter Baade was studying the stars in different regions of our galaxy and noticed something striking: not all stars were created equal. Stars in the bright, spiral arms of the Milky Way, regions full of gas, dust, and ongoing star formation, tended to be relatively young and rich in heavy elements. By contrast, the stars in older, more remote regions such as globular clusters or the galactic halo had much lower amounts of heavy elements, and they appeared to be significantly older. To categorize these differences, Baade proposed dividing stars into 2 broad groups, population 1 and population 2. Population 1 stars are the younger, metal-rich stars like our Sun. They formed after billions of years of stellar recycling, when the universe had been enriched by multiple generations of supernovae. The presence of heavy elements in their atmospheres reflects that history. Their birth clouds were laced with carbon, oxygen, silicon, iron, and countless other products of previous stellar lifetimes. These metals not only change the way a star evolves but also make it possible for planetary systems, including rocky planets like Earth, to form. Population 2 stars, on the other hand, are older, metal-poor stars. They formed when the universe was still in its youth, after the very first stars, the elusive population 3 stars, had lived and died. Population 2 stars were born from gas that had been enriched only slightly, meaning they contained far fewer heavy elements than population 1 stars. Their chemical simplicity is the cosmic equivalent of finding a handwritten note in ancient ink. It dates them to an earlier chapter in history, before the universe's chemical complexity had fully unfolded. Halo stars fall squarely into the population 2 category. Their low metallicity tells us they were forged before the Milky Way's disk had formed, when smaller, primordial galaxies were still assembling. Many of these population 2 stars are found in globular clusters, dense, spherical gatherings of ancient stars that orbit in the halo, but others wander alone, scattered across vast distances. Regardless of whether they're in clusters or solitary, their shared chemical fingerprints tie them to the early universe. Classifying a star as population 2 is not just about metallicity, it's also about context. These stars are often found in the outskirts of galaxies, in regions where star formation slowed down billions of years ago. They tend to have unusual orbital paths compared to younger stars in the disk, reflecting the fact that many were captured from other galaxies or formed in an environment very different from the one we see in the Milky Way today. The combination of low metals, unusual kinematics, and remote locations makes their identity clear. From an astronomical perspective, calling a halo star population 2 is almost like putting an age stamp on it. While we can't give an exact birth date just from the classification, we can say with high confidence that these stars are more than 10 billion years old, often closer to 12 or 13 billion. That places their formation just a few 100 million years after the Big Bang, in a universe where galaxies were still crude, irregular shapes, and the cosmic web was still knitting itself together. There's a deeper importance to this classification as well. It creates a bridge between theory and observation. We know that population 3 stars, the first generation, made entirely from Big Bang material, are thought to have been massive and short-lived, and none have yet been directly observed. The existence of population 2 stars provides indirect proof that population 3 stars once existed, because the slight metallicity of population 2 stars must have come from the supernova debris of those first giants. Without those earlier explosions, the clouds that gave birth to population 2 stars would have remained metal-free. So, in a way, halo stars are like the children of the first stars, not quite as ancient as their parents, but still unimaginably old, and carrying traces of their ancestors in their chemical makeup. By identifying them as population 2, astronomers are marking them as part of this second great wave of star formation, a wave that set the stage for everything that followed: the growth of large galaxies, the formation of complex elements, and eventually, the birth of stars like our Sun and planets like Earth. When we study halo stars under the banner of population 2, we're not just labeling them for organizational convenience, we're placing them on the grand timeline of the cosmos, assigning them to a chapter that began before our galaxy existed, when the universe was still in the raw process of building its first stellar generations. It's a reminder that these stars are not just ancient by human standards, they are ancient by the standards of the universe itself. Determining the age of a star is one of the most challenging yet fascinating tasks in astronomy. Unlike living things, stars don't carry birth certificates, and they don't leave behind fossils with datable layers. Instead, scientists have to become cosmic detectives, using every available clue, from the way a star shines to the atoms it contains, to estimate when it was born. For halo stars, these methods consistently point to a staggering conclusion: many of them are nearly as old as the universe itself. The first step in dating a star involves understanding its composition. As we discussed before, the metallicity of a star, the proportion of elements heavier than hydrogen and helium, is a critical indicator of its age. The early universe had almost no metals, and with each new generation of stars, the abundance of heavy elements increased. So when astronomers find a star with extremely low metallicity, it's a strong sign that the star formed before heavy element enrichment had progressed very far. In other words, the lower the metallicity, the closer we are to the universe's childhood years. But metallicity alone can't give an exact age. That's where stellar physics comes in. Stars evolve in predictable ways depending on their mass, composition, and the physical laws governing nuclear fusion. By studying a star's temperature, brightness, and spectrum, astronomers can place it on a diagram known as the Hertzsprung-Russell (H.R.) diagram. This chart plots stars according to their luminosity and surface temperature, revealing where they fall in their life cycle. For example, massive stars burn through their fuel quickly and leave the main sequence of the H.R. diagram in just a few million years. Smaller, cooler stars, like many halo stars, burn fuel extremely slowly and can remain on the main sequence for tens of billions of years. The position of a star on the diagram, combined with models of stellar evolution, can tell astronomers whether it's still in its youthful phase, middle age, or approaching the end of its life. Halo stars tend to be low-mass and long-lived, but that doesn't mean they are young. In fact, the opposite is true. Because they are still shining after more than 12 billion years, they must have been formed very early in the universe's history. Astronomers can verify this by comparing their properties with those of similar stars and globular clusters, whose ages can be estimated independently. Globular clusters are among the oldest structures in the galaxy, and their stars share a common formation time. By dating globular clusters through methods like main sequence fitting, comparing the brightness of their stars to theoretical models, scientists can pin down ages in the range of 12 to 13 billion years. Many halo stars match these ages closely. Another powerful tool comes from studying the abundances of certain radioactive isotopes in a star's atmosphere, a technique known as nucleocosmochronology. Some isotopes, like thorium-232 and uranium-238, decay at known rates over billions of years. By measuring how much of these isotopes remain compared to stable elements, astronomers can estimate how long it has been since the star formed. This method is delicate and requires extremely precise observations, but it has confirmed that certain halo stars are over 13 billion years old, meaning they were born when the universe itself was less than a billion years old. There's also the larger context of cosmology to consider. The universe is about 13.8 billion years old, according to measurements of the cosmic microwave background and the expansion rate of space. That sets an absolute upper limit on any star's age. So when astronomers find a halo star whose estimated age is, say, 13.2 billion years, it means that star began shining not long after the first galaxies took shape. It is as close to the beginning of time as a star can get, and still exists today. One of the most famous examples is HD 140283, nicknamed the Methuselah star. This halo star, located just 190 light-years from Earth, was measured in 2013 to have an age of about 14.46 billion years, older than the universe itself according to our best measurements. Of course, this doesn't mean the star actually predates the Big Bang. Rather, it highlights the uncertainties in stellar dating. When the uncertainties are accounted for, HD 140,283's age fits within the universe's 13.8 billion year limit, but still firmly places it among the very first stars to form after the Big Bang. It's this combination of extremely low metallicity, slow-burning nature, and consistent age measurements that cements halo stars as some of the oldest suns in existence. They have been shining for almost the entire history of the cosmos, enduring countless galactic mergers, supernova blasts, and tidal disruptions without being destroyed. Their survival across such an immense span of time is a testament not only to the stability of low-mass stars but also to the quiet persistence of cosmic relics in a universe otherwise defined by change and transformation. When we measure their ages, we're not just learning about the stars themselves, we're touching the earliest chapters of cosmic history. Each one is like a page torn from a book that was written before galaxies as we know them existed, before our sun was even a dream in the Milky Way's future, and before the elements of life were widespread. The fact that they are still here, still burning, is one of the most astonishing facts in astronomy. Long before the Milky Way settled into its familiar spiral form, the universe was a far more chaotic place, a time when galaxies were small, irregular, and constantly colliding. Theories about halo star origins often take us back to this early era, just a few 100 million years after the Big Bang, when the cosmic landscape was dominated by countless tiny protogalaxies. These were the first substantial collections of stars in the universe, clumps of matter held together by gravity, but lacking the grand, organized structures we see today. Some astronomers believe that many of the halo's ancient stars were born in these smaller, now vanished galaxies. These early galaxies would have been metal-poor by today's standards, their stars forming from nearly pristine clouds of hydrogen and helium left over from the Big Bang. Heavy elements, the so-called metals, in astronomy, only accumulate over time through successive generations of star birth and death. The lack of metals in halo stars suggests they formed before much of that cosmic enrichment had occurred, pointing to their origins in a primordial environment. As the Milky Way began to grow, its gravity pulled in and absorbed many of these small galaxies, stripping away their stars and incorporating them into a larger, more unified system. This process was not neat or instantaneous. It was a slow, messy assimilation that played out over billions of years. The remnants of these galaxies didn't blend seamlessly into the spiral disk. Instead, they were flung into the vast outer halo, where they continue to orbit to this day. In fact, when astronomers map the halo, they can still trace long, faint streams of stars that once belonged to these devoured companions. This scenario is supported by computer simulations of galaxy formation, which show that large spiral galaxies like the Milky Way are built through hierarchical assembly. In other words, by merging with smaller galaxies over time. The halo stars fit this picture perfectly. Their unusual orbits, low metal content, and sheer age all hint that they were not born inside the Milky Way as we know it, but rather were inherited from earlier building blocks of the galaxy. Some of these early star systems may have been captured intact as globular clusters, which still survive as dense knots of ancient stars in the halo. Others were torn apart completely, leaving only scattered individual stars behind. Even today, the Milky Way continues to cannibalize smaller galaxies. The Sagittarius dwarf galaxy, for example, is currently being stripped of its stars, many of which are streaming into the halo. This ongoing process is a living example of what likely happened countless times in the past. The idea that some halo stars predate the Milky Way's final form adds a fascinating twist to our understanding of galactic history. It means that these stars are not just old in an abstract sense. They are literal survivors from a time before our galaxy existed. They carry within them the story of other, now extinct galaxies, frozen in their chemical composition and orbital paths. Studying them is a bit like examining fossils from an ancient world. They are relics from a time when the cosmic environment was fundamentally different from what we see today. What's even more remarkable is that some of these stars may have been among the very first ever formed after the Big Bang. Second-generation stars born from the remains of the very first, massive, short-lived population 3 stars. Those first stars have long since vanished, but their influence lingers in the slightly enriched, yet still metal-poor, gas that formed the halo stars. This makes halo stars not just a part of Milky Way history, but a direct connection to the earliest chapters of the universe itself. By tracing the origins of these stars back to before the Milky Way's assembly, astronomers can piece together the complex story of how galaxies like ours came to be. It's a reminder that the night sky we see today is the result of billions of years of mergers, migrations, and transformations, and that far out in the quiet halo, some of the universe's oldest suns are still bearing witness to it all. If the Milky Way were a living creature, it would have the diet of a cosmic predator, and a very patient one at that. Over billions of years, our galaxy has engaged in an ongoing process of galactic cannibalism, consuming smaller galaxies and absorbing their stars, gas, and dark matter into its own structure. This is not a violent feast in the way we might imagine. The eating is driven purely by gravity, a slow but inevitable pull that draws smaller systems inward until they are completely dismantled. The concept is straightforward in theory but spectacular in scale. The Milky Way's gravitational influence extends far beyond the bright spiral disk we see in photographs, reaching deep into the surrounding dark matter halo. Any smaller galaxy that ventures too close can find itself caught in this gravitational web. As it spirals inward, tidal forces, the same kind of stretching and pulling that causes Earth's ocean tides, begin to distort the smaller galaxy, tugging its stars into elongated streams that wrap around the Milky Way. Over time, these streams become so spread out that the original galaxy loses its shape entirely, leaving its former stars scattered across the galactic halo. Astronomers have seen this process happening right now. The Sagittarius dwarf galaxy, for instance, is currently being stripped apart in a slow-motion disaster that has been unfolding for hundreds of millions of years. Its stars are spilling into long tidal tails that wrap around the Milky Way like ghostly ribbons. Another ongoing example is the Canis Major overincident, thought to be the remnants of yet another small galaxy in the midst of assimilation. These modern cases give us a direct window into the past, showing that the halo's ancient population could have been built up in much the same way. This merging history is not just a guess. The evidence is written in the orbits and chemistry of halo stars. Many stars in the halo follow strange, elongated, and tilted paths that do not match the Milky Way's disk rotation, strongly suggesting they were not born here. Their chemical fingerprints also tell the tale. Stars from different galaxies have unique elemental compositions, shaped by the specific conditions of their birth environments. By comparing these chemical signatures, astronomers can identify families of halo stars that likely came from the same long-lost galaxy. One of the most dramatic merger events in our galaxy's past is known as the Gaia Enceladus/Sausage collision. Around 8 to 10 billion years ago, the Milky Way is thought to have collided with a galaxy perhaps a quarter of its size. This ancient impact not only populated much of the halo with stars, but may have also helped thicken the Milky Way's disk and shape its current structure. The debris of this ancient galaxy still orbits the Milky Way today, its stars moving in highly radial orbits, plunging toward the galactic center, and then back out again, a motion that stands out clearly in modern sky surveys. In addition to major mergers, countless minor ones have occurred throughout our galaxy's lifetime. Each tiny galaxy swallowed added a sprinkling of stars to the halo, building it up piece by piece. This process is still ongoing. The Milky Way's future includes even bigger meals, such as the eventual collision with the Large Magellanic Cloud and much later, the grand merger with the Andromeda Galaxy. When these happen, they will trigger tidal disruptions on a scale far beyond anything in our galaxy's past, creating new halos, new star populations, and entirely new structures. From a cosmic perspective, galactic cannibalism is not sinister, it is the normal way galaxies grow. Large galaxies like ours are not born fully formed, they are assembled over time through a steady diet of smaller companions. Halo stars are the living, or rather, still burning, evidence of this process. Each one is a survivor of a merger event, a traveler from a long-vanished galaxy that now calls the Milky Way home. They are, in essence, stellar immigrants, carrying with them the history of their origins even as they orbit in a foreign land. The idea that the Milky Way is a patchwork of many former galaxies makes the halo far more than just a scattered cloud of ancient stars. It is a historical archive, an anthology of cosmic mergers, each chapter written in the light of stars that were born far away, under skies we can never see. And just as paleontologists reconstruct prehistoric worlds from fossilized bones, astronomers use these stellar remnants to piece together the untold story of our galaxy's violent, hungry past. In astronomy, the term metallicity carries a very specific and important meaning. Unlike in everyday life, where metals might bring to mind shiny, solid materials like iron or gold, astronomers use the word metals to describe all elements heavier than hydrogen and helium. This includes elements like carbon, oxygen, nitrogen, iron, and even uranium. The reason for this definition goes back to the very beginnings of the universe and the processes that forged these elements over billions of years. Right after the Big Bang, roughly 13.8 billion years ago, the universe consisted almost entirely of hydrogen and helium, with just trace amounts of lithium. There were no heavier elements at all. These simplest elements formed the first clouds of gas that collapsed under gravity to birth the very first stars, often referred to as population 3 stars. These pioneering stars were massive, short-lived, and responsible for producing the first batch of heavier elements through nuclear fusion in their cores and then scattering them across space via supernova explosions. Every subsequent generation of stars formed from gas enriched by these heavier elements, which astronomers collectively call metals. As more generations of stars lived and died, the metal content of the universe gradually increased. Stars forming in later cosmic epochs, like our Sun, are rich in metals compared to the earliest stars. This buildup of metals is crucial because it shapes the chemistry of stars, the formation of planets, and ultimately the conditions for life. Halo stars are unique in this regard because they are extremely metal poor. Their metallicity is often so low that it can be thousands of times less than that of the Sun. This scarcity of heavy elements is a telltale signature that these stars formed when the universe was still young and metal enrichment was minimal. In other words, they are living relics of an era when the cosmic chemical, periodic table, was almost empty. The near absence of metals in halo stars is not just a chemical curiosity, it's a fundamental clue to their ancient origins. Since metals are produced inside stars and spread into space only after stars explode or shed their outer layers, the very low metal content means these stars must have formed before many such enrichment events occurred. They carry the chemical imprint of an era just after the first generation of massive stars exploded and seeded the universe with the first metals, but long before the metal-rich environment of the Milky Way's disk was established. This low metallicity influences more than just the star's chemistry. It also affects its physical characteristics. Metal-poor stars tend to be bluer and hotter because metals in a star's atmosphere act as coolants, absorbing certain wavelengths of light. Without metals, radiation escapes more easily, causing subtle changes in the star's temperature and brightness. These effects help astronomers identify metal-poor halo stars among the vast stellar populations of the galaxy. Astronomers measure metallicity using spectroscopy, analyzing the light from stars to detect the unique fingerprints of various elements. By comparing the strength of absorption lines associated with metals in the star's spectrum to those in the Sun, scientists derive a value called phase/H, which quantifies the iron content relative to hydrogen. For halo stars, this ratio is often less than 1/1000 th that of the Sun, making them some of the most chemically pristine objects known. The story told by halo stars' low metallicity goes beyond the stars themselves. It's a record of cosmic history. It tells us about the conditions of the early universe, the life cycle of the first stars, and the gradual buildup of complexity that led to galaxies, planets, and eventually life. The fact that these stars still shine today, nearly unchanged in composition for over 12 billion years, makes them invaluable time capsules, offering a window into an epoch-long past. Understanding metallicity in halo stars has also helped astronomers uncover the hierarchical assembly of the Milky Way. Different groups of halo stars exhibit distinct chemical signatures, suggesting that they originated in different smaller galaxies or star clusters that merged with the Milky Way. By mapping these metallicity variations, scientists can reconstruct the galaxy's violent history of mergers and growth. In sum, the near absence of heavy elements in halo stars is one of the most compelling pieces of evidence pointing to their extreme age and primordial origins. These stars were forged from gas barely touched by the universe's first factories of matter, the earliest supernovae, making them some of the most ancient and precious relics in the cosmos. Imagine an archaeologist carefully brushing dust off an ancient fossil, piecing together fragments of bone to reconstruct a creature that lived millions of years ago. Each fossil is a portal into a lost world, a tangible remnant of history that tells a story about life, environment, and evolution on Earth. Similarly, astronomers engage in a kind of stellar archaeology, using ancient stars, especially halo stars, as cosmic fossils to reconstruct the early history of the universe. These stars, like fossils, have preserved in their composition and motion a record of events that unfolded billions of years ago, long before the formation of our solar system or even the Milky Way itself. Stellar archaeology is about more than just observing distant points of light. It is a discipline that combines physics, chemistry, and astronomy to decode the history written in the stars. Halo stars are invaluable to this pursuit because they are among the oldest surviving objects in the universe. Unlike more recent stars, whose atmospheres have been polluted by many generations of stellar recycling, halo stars preserve the elemental makeup of the early cosmos almost unchanged. Each one acts like a time capsule, carrying information about the state of the universe at the moment and place of its birth. Just as an archaeologist relies on artifacts to infer the culture and habits of ancient peoples, astronomers study the chemical abundances in halo stars to understand the processes that shape the first galaxies. When a star forms, it inherits the chemical composition of the gas cloud it condenses from. This means that the elements present in a star's atmosphere serve as a fossilized snapshot of the environment in which it was born. For halo stars, this environment was the early universe, enriched only slightly by the very first supernovae that exploded from massive population 3 stars. By measuring the abundance of various elements, from light elements like carbon and nitrogen to heavier ones like iron, magnesium, and calcium, astronomers can reconstruct the chemical fingerprint of each star. Some elements are produced in different types of supernovae or during different stages of stellar evolution. For instance, certain ratios of alpha elements, like magnesium and calcium, to iron can reveal whether the gas cloud had been enriched by rapid or slow stellar explosions. This helps astronomers not only date the star but also infer the nature of the first stars and galaxies that seeded the gas. In addition to chemistry, the motions of halo stars provide clues about their origins. By tracking their orbits, often highly elliptical and inclined relative to the galactic plane, astronomers can identify stars that likely came from other, smaller galaxies that merged with the Milky Way. These motions are like the geological layers in a dig site, telling us which stars formed in situ and which were accreted later. Combining chemical and dynamical data allows researchers to build a comprehensive narrative of how the Milky Way grew through a series of mergers and accretions. Globular clusters in the halo are also critical archaeological sites. These dense, ancient star clusters contain populations of stars with similar ages and compositions, serving as well-dated benchmarks in the timeline of galactic evolution. By studying globular clusters, astronomers gain insights into the conditions of star formation in the early universe and the processes that shaped the halo. Perhaps one of the most exciting aspects of stellar archaeology is its ability to connect with broader cosmological questions. The oldest halo stars are close in age to the universe itself, meaning they formed soon after the Big Bang. By studying them, astronomers glean information about the timing of key cosmic events, such as the reionization of the universe, the assembly of the first galaxies, and the formation of the Milky Way's dark matter halo. This makes halo stars not just relics of stellar history, but vital keys to understanding the evolution of the cosmos as a whole. Stellar archaeology also bridges the gap between theory and observation. Numerical simulations of galaxy formation predict that large galaxies grow by absorbing smaller ones, leaving behind stellar debris in the halo. Observations of halo stars, with their varied chemistry and orbital motions, confirm these predictions. In this way, each halo star acts as a fossil record that helps validate models of cosmic structure formation. The hunt for the oldest and most chemically pristine halo stars is ongoing. As telescopes and spectrographs become more advanced, astronomers are uncovering stars with even lower metallicities and more unusual chemical patterns. Some stars show unexpected enhancements of carbon or other elements, hinting at exotic processes in the early universe or the influence of rare types of supernovae. Each new discovery challenges and refines our understanding of the first stellar generations. The importance of stellar archaeology extends beyond professional astronomy. It touches on profound philosophical questions about our place in the universe. These ancient stars have been shining continuously for nearly 13 billion years, long before Earth existed, before the Sun was born, and before any life as we know it could arise. They are silent witnesses to the grand story of cosmic evolution, from the simplicity of the Big Bang to the complexity of galaxies, stars, planets, and ultimately ourselves. In conclusion, just as fossils tell the story of Earth's biological past, halo stars provide a fossil record of the universe's earliest epochs. Through the meticulous study of their chemical signatures, motions, and locations, astronomers perform stellar archaeology, piecing together the formation of galaxies, the life cycle of stars, and the unfolding of cosmic history. These ancient suns are not merely distant points of light. They are time machines carrying the memory of the cosmos's youth, offering an invaluable glimpse into the origins of everything we see today. Among the countless stars scattered throughout the Milky Way's halo, A select few stand out as truly extraordinary, stars whose ages approach the very dawn of time itself. One of the most remarkable of these ancient suns is SMSS J031300.36, 670839.3, often abbreviated simply as SMSS J0313-6708. This star is a cosmic relic from an era more than 13 billion years ago, formed when the universe was barely a few 100 million years old. Its discovery has provided astronomers with a rare and invaluable window into the infancy of the cosmos and the birth of the first generations of stars. SMSS J0313-6708 was discovered relatively recently, in 2014, by a team of astronomers using the SkyMapper Southern Sky Survey, a project designed to map the southern hemisphere of the sky with unprecedented detail. When the data from this survey revealed a star with extremely peculiar properties, it sparked immense excitement in the astronomical community. This star's chemical fingerprint was unlike anything seen before, showing an extraordinarily low abundance of metals, especially iron, which is typically one of the most detectable elements in stars. The metallicity of SMSS J0313-6708 is so low that it has been described as the most metal-poor star known to date. It contains less than 1/10,000,000th the amount of iron compared to the Sun. To put this into perspective, if the Sun's iron content were represented by a gallon of water, the amount of iron in SMSS J0313-6708 would be roughly equivalent to a single drop. Such an extreme lack of heavy elements tells us that this star formed before the universe had been enriched by many generations of supernova explosions. It is almost certainly a second-generation star, born from gas polluted by the very first, massive population 3 stars that exploded as supernovae. But what makes SMSS J0313-6708 even more fascinating is what its chemical makeup reveals about those first stars. Its atmosphere is enriched in elements like carbon and magnesium but nearly devoid of heavier elements such as iron. This unusual pattern matches theoretical predictions of nucleosynthesis, the creation of elements inside stars, by the earliest supernovae, especially those involving so-called faint supernovae, which released lighter elements but trapped much of their heavier material inside a collapsing core. This insight allows astronomers to reconstruct the explosive death of the first stars by studying the elemental fingerprints left in stars like SMSS J0313-6708. The star acts like a cosmic Rosetta Stone, translating the violent chemistry of the universe's dawn into something we can observe and understand. Determining the exact age of SMSS J0313-6708 is inherently challenging. Since stars don't carry timestamps, astronomers rely on indirect methods such as measuring their chemical compositions, their position on the Hertzsprung, Russell diagram, and their motions through the galaxy. From these data, combined with theoretical models of star formation and cosmic evolution, scientists estimate that SMSS J0313-6708 is likely over 13 billion years old, placing it among the oldest known stars in the universe. This immense age means that SMSS J0313-6708 formed just a few 100 million years after the Big Bang. It witnessed the universe's first epochs of star formation, the assembly of the earliest galaxies, and the slow buildup of complex elements that would eventually seed the formation of planets and life. Interestingly, this star is located in the halo of the Milky Way, hundreds or even thousands of light years above the galaxy's disk, orbiting through a vast and mostly invisible region of space. This location is consistent with the idea that many ancient stars did not form in the Milky Way's disk itself but were brought in through the accretion of smaller galaxies or formed in the galaxy's primordial halo. SMSS J0313-6708 is not the only ancient halo star to awe astronomers. Stars like He 1523-0901 and BD plus 44°493 have similarly low metallicities and ancient ages, and they too offer clues to the early universe's conditions. However, SMSS J0313-6708's extreme chemical purity and rarity make it a standout object of study. Beyond age and chemistry, These stars challenge and refine our models of cosmic evolution. They show that star formation and supernova nucleosynthesis in the early universe were more complex and varied than once thought. Some of the first stars may have died quietly in faint supernovae, leaving behind metal-poor gas from which stars like SMSS J0313-6708 could form. Others exploded in more energetic events, distributing heavier elements more widely. Studying the oldest halo stars also has profound implications for understanding the Milky Way's formation. Their presence in the halo, along with their unique chemical signatures, supports the theory that the Milky Way grew by cannibalizing smaller galaxies, each bringing its own ancient stellar population. These stars are remnants of those primordial systems, locked into orbits that preserve their history. Moreover, the discovery of stars like SMSS J0313-6708 pushes the limits of modern observational technology. Detecting and analyzing such faint, metal-poor stars requires incredibly sensitive instruments and large telescopes capable of high-resolution spectroscopy. Projects like the SkyMapper survey, the Gaia mission, and the upcoming James Webb Space Telescope continue to expand our ability to find and study these cosmic relics. In philosophical terms, the existence of stars like SMSS J0313-6708 is humbling. It forces us to confront the vastness of time and space. This star began shining billions of years before our solar system existed, and it has endured countless cosmic events while silently orbiting in the galactic halo. It is a living connection to the universe's earliest moments, a celestial time capsule that tells the story of creation itself. The study of SMSS J0313-6708 and its peers is ongoing. As astronomers gather more data and refine their models, these ancient stars continue to shed light on the origins of elements, the formation of the first galaxies, and the processes that set the stage for the universe we inhabit today. In conclusion, stars like SMSS J0313-6708 are among the oldest known objects in the cosmos, providing an extraordinary glimpse into the universe's infancy. Their extreme age and pristine chemical makeup make them invaluable to our understanding of cosmic history, stellar evolution, and galactic formation. Through their study, we are able to trace a line from the Big Bang to the present, connecting the birth of the universe to the starry sky we see today. When we gaze up at the night sky, the bright, familiar glow of our sun feels eternal and unchanging. It is the anchor of our solar system, the source of warmth and light that sustains life on Earth. Yet, in the grand timeline of the universe, our sun is a relative newborn, a youthful star in a cosmos filled with ancient suns whose light began shining billions of years before the first planets even existed. Comparing the sun's age to that of halo stars reveals just how young our solar system really is, and it invites us to reflect on the vastness of cosmic time. The sun formed approximately 4.6 billion years ago, emerging from a collapsing cloud of gas and dust within the Milky Way's disk. This process gave birth not only to the sun but also to the planets, moons, asteroids, and comets that comprise our solar system. Our star belongs to what astronomers call population 1 stars, relatively young stars that contain higher amounts of metals, or elements heavier than hydrogen and helium. These metals are essential because they contribute to planet formation and even the chemistry necessary for life. In contrast, many halo stars have ages exceeding 12 to 13 billion years, making them nearly 3 times as old as the Sun. These ancient stars formed in a universe that was still in its infancy, a cosmos vastly different from the one we know today. The gas clouds from which halo stars arose were nearly pristine, containing very few elements beyond hydrogen and helium. Over time, the products of stellar fusion and supernova explosions enriched the interstellar medium with heavier elements, allowing later generations of stars like the Sun to form with more complex chemistry. This difference in age has profound implications. The Sun's birth came after several generations of stars had already lived and died, enriching the galaxy with the metals necessary for rocky planets to form. In fact, without the earlier generations of massive, short-lived stars, many of which are now extinct, the solar system's raw materials simply would not have existed. This makes the Sun a product of a long cosmic heritage, but it also highlights that it is relatively young when compared to the universe itself. Beyond age, the physical properties of halo stars and the Sun differ significantly. Halo stars are often less massive and have lower metallicities, which means they burn fuel differently and can live much longer than stars like the Sun. Many halo stars are low mass, cool, and stable, allowing them to survive for tens of billions of years. The Sun, by contrast, is a medium-mass star with an expected total lifetime of about 10 billion years, roughly half of which it has already spent shining. This means that while the Sun is in its middle age, many halo stars have existed far longer and will likely outlive the Sun by several billions of years. These ancient stars are like elderly witnesses to the universe's history, whereas the Sun is still relatively youthful, shining brightly but destined to evolve and ultimately perish long before some of these halo stars reach the end of their lifespans. The comparison also underscores the dynamic and evolving nature of galaxies like the Milky Way. Our galaxy is not static. It is a living system continually forming new stars while harboring ancient stellar populations. The Sun and its solar system occupy the galactic disk, a younger, more metal-rich environment conducive to planet formation and complex chemistry. Meanwhile, the halo is a vast, sparsely populated region where the oldest stars reside, relics of an earlier era. Reflecting on these timescales deepens our understanding of cosmic evolution. The difference between the Sun's 4.6 billion years and the 13 billion year ages of halo stars is not merely a numerical gap. It represents an entire epoch of cosmic history during which the universe transformed from a simple, hot plasma to a richly structured realm filled with galaxies, stars, and planets. For humanity, this comparison is humbling. It places our solar system's existence within the broader tapestry of cosmic time, reminding us that our origins are relatively recent in the grand scheme. The light from ancient halo stars began its journey long before Earth formed, traversing the void for billions of years to reach us today. The Sun's youth relative to halo stars also explains why the solar system contains a diverse range of elements necessary for life. The metals forged in earlier stars were recycled through countless cosmic cycles, enriching the material that eventually coalesced into our planets. Without this chemical evolution, Earth and its biosphere might never have existed. In this way, the Sun and halo stars represent two distinct chapters in the universe's story, the ancient and the relatively modern, the primordial and the evolved. Studying both allows astronomers to piece together a more complete picture of how galaxies grow and change over time, how stars are born, live, and die, and how the ingredients for life accumulate across cosmic epochs. Ultimately, the contrast between the Sun and the oldest halo stars is a testament to the vastness of cosmic time and the ongoing cycle of stellar birth and death. It invites us to appreciate not only our place in the universe but also the deep history that preceded our existence, a history written in the light of stars that have been shining for nearly the entire age of the cosmos. Unlike the stars that dominate the bright, swirling disk of the Milky Way, which mostly follow nearly circular orbits around the galactic center, halo stars exhibit markedly different and far more complex patterns of motion. These ancient suns often travel along long, elliptical orbits that carry them far above and below the galactic plane, weaving through the vast, diffuse halo region in paths that can seem chaotic when compared to the orderly rotations of disk stars. Understanding these unique orbital characteristics reveals much about the history and structure of our galaxy, and the ancient origins of the halo population. The Milky Way's disk is a flattened, spinning structure composed of billions of stars, including our Sun, moving in roughly the same direction in nearly circular orbits. This rotation creates the familiar spiral arms and defines the galaxy's visible shape. Stars in the disk are relatively young, metal-rich, and tightly bound to this planar structure. Their orbits keep them close to the galactic plane, typically within a few hundred light-years above or below it, resulting in a relatively thin, flat distribution of stars. In contrast, halo stars are scattered in a spherical distribution around the galaxy's center. Their orbits are highly inclined, often plunging through the galactic plane at steep angles, and their paths are typically far more eccentric, meaning elongated rather than circular. A halo star might spend much of its time tens of thousands of light-years above the galactic disk, then swoop down through the dense central regions before arcing back out again. This vast range of motion allows halo stars to explore the full three-dimensional space around the Milky Way, unlike disk stars restricted to a narrow, flat orbit. These elongated, elliptical orbits can be visualized as stretched loops or ovals, differing greatly in shape and orientation. Some halo stars follow polar orbits that take them almost perpendicularly over the galactic poles, while others travel in retrograde orbits, moving opposite to the galaxy's overall rotation. Such diverse and sometimes chaotic motions stand in stark contrast to the relatively ordered, circular orbits within the disk, underscoring the halo star's distinct origins. One reason for these unusual orbits is the complex formation history of the Milky Way's halo itself. Many halo stars did not form within the galaxy's disk but were instead accreted from smaller galaxies that merged with the Milky Way in the distant past. When a dwarf galaxy is gravitationally torn apart by the Milky Way, its stars are stripped and injected into the halo, inheriting a variety of orbital paths based on the merger's dynamics. These stars retain the memory of their original systems and their motions, resulting in the diverse orbital shapes seen today. Because the halo is dominated by such accreted stars, their orbits often do not align with the Milky Way's rotation. Instead, their paths can be highly inclined, retrograde, or eccentric. These characteristics allow astronomers to identify groups of halo stars that share similar orbital patterns, tracing them back to their progenitor galaxies or star clusters. This technique is a cornerstone of galactic archaeology, enabling the reconstruction of the Milky Way's assembly from smaller building blocks. Moreover, some halo stars belong to stellar streams, long, ribbon-like trails of stars that are remnants of tidally disrupted dwarf galaxies or globular clusters. These streams follow coherent orbits through the halo, mapping out the gravitational potential of the Milky Way and providing clues about dark matter distribution. The orbits of stars in these streams are often highly elongated and tilted relative to the galactic plane, reflecting the original trajectory of their parent systems before disruption. The study of halo star orbits also reveals insights about the Milky Way's dark matter halo, the vast, invisible envelope of dark matter that dominates the galaxy's mass. By measuring the velocities and trajectories of halo stars, astronomers can infer the shape, extent, and density profile of this elusive component. For example, the fact that halo stars move in extended, eccentric orbits supports the existence of a massive, roughly spherical dark matter halo that envelopes the galaxy, exerting gravitational influence far beyond the visible disk. One striking feature of halo star motions is their high velocity dispersion, a measure of the range of speeds among stars in a given population. Unlike the disk, where stars move in a relatively narrow range of velocities around the galaxy's rotation speed, halo stars display a broad spread of velocities, including some moving very fast relative to the galactic center. This velocity spread is a hallmark of a dynamically hot population, reflecting the turbulent and chaotic history of the halo's assembly. The orbits of halo stars also evolve over time due to gravitational interactions within the galaxy. Close encounters with massive structures such as giant molecular clouds, spiral arms, or the central bar can perturb their trajectories, causing gradual changes in orbital eccentricity and inclination. However, the overall elliptical nature of their orbits remains a defining characteristic. In summary, the orbits and motions of halo stars are unlike those of stars in the galactic disk, marked by high eccentricity, large inclination angles, and often retrograde directions. These unusual paths are living evidence of the Milky Way's history of mergers and accretion, preserving the dynamical signatures of galaxies long absorbed into its halo. By studying the motions of halo stars, astronomers not only learn about the stars themselves but also about the invisible scaffolding of dark matter, the processes that formed our galaxy, and the cosmic environment billions of years ago. This fascinating dynamical behavior makes halo stars invaluable tools for probing the Milky Way's formation and structure, turning the galaxy's halo into a sprawling archaeological site, with stellar orbits tracing the echoes of ancient cosmic events. As new data from missions like Gaia continue to refine our understanding of these stellar motions, the story of the Milky Way's assembly becomes ever clearer, revealing a galaxy shaped by gravity, time, and countless ancient stars on timeless journeys. The structure of the Milky Way galaxy is beautifully complex, composed of multiple overlapping components that each tell a different chapter of its formation and evolution. Among these components, the thin disk, the thick disk, and the halo stand out as key stellar populations, each with distinct characteristics in terms of age, composition, motion, and origin. While halo stars are often ancient, metallic, and scattered in elliptical orbits around the galaxy, stars in the thick and thin disks represent different evolutionary stages and environments. Comparing the thick disk stars to halo stars, and contrasting both with the thin disk, reveals much about how the Milky Way grew and changed over billions of years. The thin disk is the most familiar component to us because it includes the Sun and the majority of stars visible in the night sky. This disk is relatively flat, thin, about 300 to 400 parsecs thick, and packed with young to middle-aged stars. These stars tend to be metal-rich, containing higher abundances of heavy elements forged by many generations of star formation. The thin disk hosts the well-known spiral arms, where ongoing star formation takes place, creating bright clusters, nebulae, and a dynamic environment rich in gas and dust. Moving upward and outward from the thin disk, astronomers identify a thicker, more diffuse component known as the thick disk. This structure is roughly 1,000 to 3,000 parsecs thick, several times thicker than the thin disk, and contains stars that are on average older, more metallic, and with different kinematics. Thick disk stars are often classified as population 2 stars, although this category can overlap somewhat with halo stars in terms of age and metallicity. These stars are generally older than thin disk stars but younger than the most ancient halo stars. One key difference between thick disk stars and halo stars lies in their orbits and motions. Thick disk stars orbit the galactic center in more circular paths, similar to thin disk stars but with greater vertical excursions above and below the galactic plane. Their orbits are inclined relative to the thin disk, but not as extreme or eccentric as those of halo stars. While thin disk stars tend to stay close to the galactic plane, thick disk stars venture several thousand light-years above it, moving with higher velocities and more random directions. This gives the thick disk a puffier, more spheroidal shape compared to the razor-thin thin disk. The halo stars, in stark contrast, inhabit a vast, roughly spherical region that extends tens of thousands of light-years above and below the galactic plane. Their orbits are often highly eccentric and inclined, frequently retrograde, opposite the galaxy's rotation, and much less orderly. These characteristics reflect their origins as remnants of smaller galaxies devoured by the Milky Way or as relics of the primordial stellar population formed before the disk itself. Chemical composition further distinguishes these populations. Thick disk stars generally have moderate metallicity, lower than that of the thin disk but higher than halo stars. They show enhanced ratios of alpha elements, like magnesium and calcium, relative to iron, indicating that they formed in environments with rapid star formation dominated by Type II supernovae. In comparison, halo stars exhibit very low metallicities and varied elemental abundances that often point to enrichment from early, possibly faint supernovae and primordial nucleosynthesis. The thick disk is believed to have formed during an early, turbulent period of the Milky Way's history, possibly triggered by a major merger event or internal dynamical heating. These violent processes would have puffed up the early thin disk, scattering stars into higher orbits and increasing velocity dispersions, creating the thick disk component we see today. This scenario explains why thick disk stars are older and have higher velocity dispersions than thin disk stars, but are still more orderly than halo stars. Halo stars, on the other hand, are thought to be largely accreted from dwarf galaxies or formed in situ during the initial collapse of the protogalactic cloud. Their chaotic, elongated orbits and extremely low metallicities are signatures of this ancient, complex origin. In this sense, the halo represents the Milky Way's extended stellar fossil record, while the thick and thin disks trace more recent phases of star formation and galactic evolution. Studying these populations provides astronomers with a layered understanding of the galaxy's past. The thin disk reveals the current environment and ongoing processes. The thick disk preserves the memory of early, energetic events, and the halo contains the oldest remnants of the Milky Way's formative years. By comparing the ages, chemical compositions, and motions of stars in each component, scientists piece together the timeline of the galaxy's assembly and growth. For example, stars in the thick disk typically range in age from 8 to 12 billion years, while halo stars often exceed 12 billion years, making them nearly as old as the universe itself. The thin disk stars, including the Sun, are generally younger than 8 billion years. This age gradient aligns with the chemical evolution observed in each population, supporting the picture of a galaxy that formed inside out and grew through hierarchical mergers. In conclusion, while halo stars are ancient, metal-poor wanderers tracing eccentric orbits far above and below the galactic plane, thick disk stars occupy a somewhat younger, more metal-rich, and dynamically calmer population that still ventures beyond the thin disk but remains more closely tied to the Milky Way's rotation. These distinctions in origin, motion, and chemistry reflect the galaxy's layered history, revealing how the Milky Way has evolved from a chaotic early state into the structured spiral we call home. Scattered throughout the vast, sparsely populated halo of the Milky Way are some of the most awe-inspiring and ancient stellar structures in our galaxy: globular clusters. These dense, spherical collections of stars serve as stellar time capsules, preserving an extraordinary record of the early universe. Their presence in the halo not only enriches its stellar population but also provides critical clues to the formation, evolution, and assembly history of the Milky Way itself. Globular clusters are tightly bound groups containing anywhere from tens of thousands to millions of stars packed into a relatively small, spherical volume, often just a few dozen light-years across. Unlike the more loosely arranged stars in open clusters, which tend to be young and found primarily in the galactic disk, globular clusters are overwhelmingly ancient. Many are nearly as old as the universe, with ages ranging from about 10 to 13 billion years. They are dominated by population II stars, characterized by low metallicity and an old age, similar to the halo field stars but existing as dense, gravitationally bound systems. These clusters orbit the Milky Way in the halo, moving along extended, often elliptical orbits that take them far above and below the galactic plane. Their distribution is roughly spherical around the galactic center, and they are among the most visible constituents of the halo because their combined light can be observed even at great distances. The role of globular clusters in the halo is multifaceted. First, they act as fossil records of the early stages of star formation and galaxy assembly. Their great age means they formed during or shortly after the epoch of reionization, the period when the first stars and galaxies ignited, transforming the universe from a dark, neutral state into a luminous one. Because globular clusters are densely packed, their stars formed nearly simultaneously from the same primordial gas cloud, preserving a uniform chemical signature that astronomers can study to understand the conditions of early star formation. Secondly, globular clusters serve as dynamical tracers of the Milky Way's gravitational potential. Because they orbit through the halo and reach large distances from the galactic center, measuring their positions and velocities allows astronomers to map the distribution of both visible matter and the elusive dark matter halo enveloping the galaxy. The motions of globular clusters help reveal the shape, mass, and extent of the Milky Way's dark matter halo, which dominates the galaxy's total mass but cannot be observed directly. In addition, globular clusters offer insights into the galaxy's merger history. Many globular clusters exhibit properties that suggest they originated not in the Milky Way itself but in dwarf galaxies that were later cannibalized and absorbed. Some clusters have orbital patterns and chemical compositions distinct from typical Milky Way clusters, indicating an extragalactic origin. Studying these, accreted clusters helps astronomers reconstruct the timeline and scale of galactic mergers, revealing how the halo grew over billions of years by assimilating smaller stellar systems. One famous example is the Omega Centauri cluster, the largest and most massive globular cluster associated with the Milky Way. It contains millions of stars and shows evidence of multiple stellar populations with varied chemical abundances, hinting that it might be the remnant core of a dwarf galaxy disrupted by the Milky Way's gravity. Such clusters blur the lines between star clusters and dwarf galaxies, illustrating the complexity of the halo's formation. The dense environments of globular clusters also make them natural laboratories for studying stellar evolution and dynamics. The stars within them interact gravitationally in ways not common in less crowded environments, leading to phenomena such as stellar collisions, binary formation, and exotic objects like millisecond pulsars and blue stragglers. By observing these processes, astronomers gain deeper understanding of how stars evolve in extreme conditions, complementing studies of isolated stars in the disk or halo field. From a broader perspective, globular clusters help address fundamental cosmological questions. Their extreme ages provide lower bounds on the age of the universe, independently confirming estimates derived from cosmic microwave background measurements and other cosmological probes. Their chemical compositions shed light on the nucleosynthesis processes that operated in the first generations of stars and the subsequent enrichment of the interstellar medium. The discovery and study of globular clusters have been greatly enhanced by modern telescopes and surveys. Instruments like the Hubble Space Telescope have resolved individual stars within clusters, allowing detailed photometric and spectroscopic analysis. Large surveys and missions such as Gaia have measured precise positions and motions, enabling the reconstruction of cluster orbits and their connection to the Milky Way's structure. In recent years, astronomers have also begun to uncover new globular clusters and stellar streams associated with disrupted clusters, further enriching our knowledge of the halo's complexity. Some clusters have been linked to specific merger events, connecting them to identifiable progenitor galaxies that built up the halo through hierarchical accretion. In conclusion, globular clusters are essential components of the Milky Way's halo, acting as dense, ancient stellar archives that illuminate the early history of star formation and galaxy assembly. Their properties, motions, and compositions provide a wealth of information about the origin and evolution of our galaxy, the nature of dark matter, and the processes shaping the cosmos over billions of years. These spectacular clusters are not only beautiful celestial jewels but also fundamental keys to unlocking the secrets of the universe's earliest days. The formation of the Milky Way's galactic halo remains one of the most fascinating and actively researched topics in astronomy, as it holds the key to understanding not only the history of our galaxy but also the broader processes of cosmic structure formation. The halo, a vast, roughly spherical region surrounding the galaxy, populated by ancient stars, globular clusters, and dark matter, has a complex origin story woven from multiple formative events spanning billions of years. Two main theoretical frameworks have emerged to explain how the halo formed: the early monolithic collapse model and the hierarchical merger, or accretion model. Today, the prevailing view incorporates elements of both, illustrating a dynamic and evolving picture of the Milky Way's growth. The early monolithic collapse theory was first proposed in the mid-20th century by the astronomer Egan, Lynden-Bell, and Sandage, often referred to as the ELS model. According to this scenario, the halo formed rapidly and relatively early from the gravitational collapse of a large, nearly spherical cloud of primordial gas. As this protogalactic cloud collapsed, it condensed and fragmented into stars and star clusters, which eventually settled into the galaxy's disk and halo components. In this view, halo stars formed in situ, that is, within the collapsing cloud itself, making the halo one of the galaxy's oldest structures. The stars produced by this collapse are typically metal-poor and orbit in a wide variety of directions and eccentric orbits, reflecting the chaotic dynamics of the initial collapse. This model accounts for many observed features of halo stars: their low metallicities, high velocity dispersions, and random orbital inclinations. It also explains why the halo is roughly spherical, in contrast to the flattened disk, which formed later as the gas settled into a rotationally supported structure. However, the monolithic collapse model alone struggles to fully explain the detailed chemical and dynamical substructures observed in the halo today. This is where the hierarchical merger model, rooted in the cold dark matter cosmology, becomes critical. According to this framework, galaxies like the Milky Way grew over time by accreting smaller galaxies and star clusters, effectively cannibalizing their neighbors through gravitational interactions. This process, known as hierarchical structure formation, is supported by both theoretical simulations and observational evidence. In this picture, the galactic halo is largely composed of stars and clusters that were originally part of smaller satellite galaxies orbiting the Milky Way. Over billions of years, these satellites were disrupted by tidal forces, and their stars were stripped and assimilated into the halo, creating a rich mosaic of stellar streams, substructures, and chemically distinct populations. Some halo stars formed in situ, but a significant fraction originated elsewhere, making the halo a dynamic and composite stellar population. The Gaia mission and large spectroscopic surveys have provided compelling evidence for this merger-driven assembly. They have identified multiple stellar streams, remnants of disrupted dwarf galaxies and globular clusters, crisscrossing the halo, each with unique chemical signatures and orbital properties. Some of these streams correspond to relatively recent accretion events, while others trace back to ancient mergers. One prominent example is the Gaia Enceladus or Sausage Galaxy, a dwarf galaxy that merged with the Milky Way around 10 billion years ago, contributing a substantial population of stars to the inner halo. The two formation scenarios are not mutually exclusive but rather complementary. The galactic halo likely began forming through the early collapse of primordial gas, creating an initial population of ancient stars. This was followed and enriched by successive merger events that brought in additional stars and globular clusters from smaller galaxies. The relative contributions of these processes vary spatially within the halo. The inner halo may contain more in-situ stars formed during the early collapse, while the outer halo is dominated by accreted populations. Further complexities arise from the presence of dark matter, which dominates the galaxy's mass and influences its formation history. Dark matter halos surrounding the Milky Way provided the gravitational wells in which gas could cool and form stars. The interactions between baryonic matter, normal matter, and dark matter during mergers shaped the halo structure, influencing star orbits and the distribution of globular clusters. In sum, the Milky Way's halo is a cosmic patchwork quilt, stitched together by both rapid early collapse and the slow, steady accretion of smaller galaxies over billions of years. This layered formation history is reflected in the chemical diversity, orbital dynamics, and spatial distribution of halo stars and clusters. Ongoing observations and simulations continue to refine our understanding, revealing a galaxy shaped by both violent beginnings and a complex assembly process. This nuanced view underscores the Milky Way as a living system, constantly evolving and growing, with its halo serving as a stellar archive of its most ancient and dramatic chapters. Among the most profound mysteries in astrophysics is the nature of the very first stars, often called population 3 stars, that formed shortly after the Big Bang, during the cosmic dawn when the universe was emerging from darkness into light. These primordial stars were forged from pristine gas composed almost exclusively of hydrogen and helium, the simplest elements created during the Big Bang nucleosynthesis. Unlike later generations of stars, population 3 stars contained virtually no metals, elements heavier than helium, making their formation, life cycles, and deaths fundamentally different from stars we observe today. While direct observations of these first stars remain elusive due to their great age and distance, a tantalizing possibility is that many of the ancient stars populating the Milky Way's halo are direct descendants, or stellar fossils, second-generation stars born from gas enriched by the first star's explosive deaths. The concept that halo stars may be remnants of the universe's very first stars arises from their unique chemical signatures and extreme ages. The earliest stars likely formed within a few 100 million years after the Big Bang, at a time when the universe was still very young, less than 5% of its current age. These first stars are believed to have been massive, some hundreds of times the mass of the Sun, because the metal-free primordial gas cooled inefficiently, favoring the formation of large, hot stars. These titanic stars burned quickly and died as supernovae or even hypernovae, synthesizing and dispersing the first heavy elements, carbon, oxygen, iron, and beyond, into their surroundings. Second-generation stars, including many halo stars, formed from clouds of gas enriched by this first wave of supernovae. Because these stars formed from gas containing traces of the first star's heavy elements, but still very metal-poor, Their chemical fingerprints encode the nucleosynthesis processes of their predecessors. By studying the abundances of elements in halo stars, astronomers can infer properties of the first stars, such as their masses, lifetimes, and explosion mechanisms. One of the strongest lines of evidence linking halo stars to population 3 stars comes from the study of extremely metal-poor (EMP) stars. These stars have extraordinarily low iron content, often less than 1/10,000th that of the Sun, and show elemental abundance patterns predicted by models of early supernovae. For example, enhanced carbon and magnesium ratios coupled with depleted heavier elements suggest formation from gas polluted by faint or mixing and fallback supernovae, types of explosions theorized to occur in the first stars. The famous halo star SMSS J031300.36 670839.3, discussed earlier, is a prime example of such a relic. Its chemical makeup matches predictions for gas enriched by a single population 3 supernova, making it a near-pristine fossil from the cosmic dawn. This star's existence confirms that second-generation stars can survive for billions of years, serving as windows into the universe's earliest epochs. Understanding these ancient stars also helps address questions about the initial mass function, IMF, of population 3 stars, essentially, the range and distribution of their masses. Since no population 3 stars have yet been directly observed, the chemical signatures preserved in halo stars provide one of the few indirect methods to constrain their characteristics. For instance, the relative abundance of elements like carbon, nitrogen, and oxygen in halo stars reflects the nucleosynthetic yields of the first stars and their explosion energies. Another fascinating aspect is the role these first stars played in the reionization of the universe. Their intense ultraviolet radiation ionized the surrounding hydrogen gas, ending the cosmic, dark ages, and allowing light to travel freely through space. By studying halo stars and reconstructing their progenitors, astronomers can piece together how early star formation drove these monumental changes in the universe's structure. The survival of low-mass halo stars over 13 billion years also informs stellar evolution theory. While the first stars were likely massive and short-lived, their lower-mass descendants, born from enriched gas, could burn hydrogen slowly enough to survive to the present day. These survivors are the ancient halo stars we observe, frozen in time and offering invaluable clues about the primordial universe. However, several challenges complicate this picture. Because the first stars were so massive, they probably died before any low-mass population 3 stars could form. This means that true population 3 stars may no longer exist, having exhausted their fuel long ago. The halo stars we see are thus second generation, or later, formed after some metal enrichment. Disentangling these generations requires careful spectroscopic analysis and detailed modeling. Moreover, the hierarchical nature of galaxy formation implies that some halo stars originated in smaller, primitive galaxies that merged with the Milky Way. These progenitor systems may have had their own star formation histories, complicating the task of linking individual halo stars directly to the first stars. Still, by combining kinematic data from missions like Gaia with chemical abundances, astronomers can identify groups of stars likely sharing common origins, some tracing back to the earliest times. The study of halo stars as remnants of the first stars is a vibrant and evolving field. Future telescopes like the James Webb Space Telescope, JWST, and the upcoming Nancy Grace Roman Space Telescope aim to push the observational frontier, potentially detecting the direct signatures of population 3 star formation in distant, young galaxies. Meanwhile, continued spectroscopic surveys of the Milky Way's halo will expand the catalog of extremely metal-poor stars, refining our understanding of early nucleosynthesis and stellar evolution. In essence, halo stars act as cosmic archaeologists' tools, preserving in their atmospheres the elemental relics of the universe's earliest chapters. Their existence bridges the gap between the mysterious population 3 stars, whose direct light we may never see, and the rich, chemically evolved universe we inhabit today. By unlocking their secrets, we gain insight not only into the origins of the Milky Way but into the dawn of all stellar light, the first seeds of cosmic complexity, and the processes that set the stage for everything that followed. The ancient halo stars scattered throughout our Milky Way are far more than just distant points of light. They are living archives of cosmic history, meticulously preserving the conditions and processes that shaped the early universe. Acting much like time capsules or stellar fossils, these stars encode invaluable information about the physical environment, chemical evolution, and galactic dynamics spanning nearly the entire 13.8 billion-year history of the cosmos. By studying them, astronomers gain unique insights into a time long before the formation of our solar system, before the emergence of complex life, and even before the full assembly of our galaxy. One of the most profound implications of these ancient stars is their role as chemical records of the universe's infancy. The elements within a star's atmosphere reflect the composition of the gas cloud from which it formed. Unlike the Sun or younger stars that formed in chemically enriched environments, halo stars often contain extremely low amounts of metals, elements heavier than hydrogen and helium. These low metallicity signatures provide a direct glimpse into the primordial chemical abundances shortly after the Big Bang. By analyzing the detailed chemical abundances in halo stars, scientists can trace the nucleosynthesis pathways that occurred in the earliest generations of stars. For example, the relative ratios of alpha elements, like magnesium, silicon, and calcium, to iron offer clues about the types of supernovae that enriched the gas before the halo stars formed. These ratios help distinguish contributions from massive stars exploding as core-collapsed supernovae versus white dwarfs undergoing thermonuclear explosions. Such detailed, chemical fingerprinting reveals the timescales and processes that govern star formation and element creation in the young universe. Furthermore, halo stars provide constraints on the initial mass function, IMF, of the first stars. The IMF describes the distribution of masses of stars formed in a given stellar population. Since the earliest stars were probably massive and short-lived, the chemical signatures preserved in halo stars indicate how quickly heavy elements were injected into the interstellar medium, and how this influenced subsequent star formation. Understanding the IMF in the early universe sheds light on fundamental questions about galaxy formation, cosmic reionization, and the seeding of life-essential elements. Beyond chemistry, the motions and spatial distribution of halo stars act as dynamical tracers of the Milky Way's formation and evolution. Their wide-ranging, eccentric orbits and clustering into streams or groups reflect the accretion of smaller galaxies and star clusters, providing a living map of past merger events. These kinematic records allow astronomers to reconstruct the galaxy's assembly history, including the timing, mass, and origin of progenitor systems that built the halo over billions of years. On a cosmological scale, the ages of halo stars serve as independent clocks that help confirm the age of the universe. Their extreme antiquity, many being over 13 billion years old, places lower limits on the universe's age, consistent with measurements from cosmic microwave background radiation and the expansion rate of space. These stars thus offer a cross-check for cosmological models and parameters. Additionally, halo stars inform our understanding of the early dark matter distribution. Since their motions are influenced by the gravitational pull of both visible and invisible matter, analyzing their orbits helps constrain the shape, density, and extent of the Milky Way's dark matter halo. This, in turn, impacts models of galaxy formation and the nature of dark matter itself. The implications of studying halo stars extend to the concept of galactic archaeology, where astronomers act like cosmic detectives, piecing together the history of the Milky Way through its oldest constituents. Just as terrestrial archaeologists analyze ancient artifacts to reconstruct human history, astronomers analyze the chemical and dynamical properties of halo stars to reconstruct the universe's formative epochs. Moreover, the very survival of these stars for billions of years suggests that low-mass, metal-poor stars have extraordinarily long lifespans. This longevity means that some halo stars may outlive the Sun and even the expected lifetime of the universe's current phase, offering a continuous record stretching from the cosmic dawn to the far future. By studying halo stars in our own galaxy and comparing them with similar ancient stars found in neighboring galaxies like Andromeda, astronomers gain a broader cosmological context, understanding how universal processes govern galaxy evolution across the cosmos. In conclusion, ancient halo stars are not merely relics. They are active storytellers narrating the saga of the universe's earliest times. Their chemical compositions, ages, and motions are invaluable records of the conditions prevailing shortly after the Big Bang, the first waves of star formation, and the complex dance of galactic assembly. Through their light, we can peer back billions of years, unraveling the cosmic tapestry that ultimately led to the creation of our solar system, Earth, and life itself. One of the most profound and fascinating aspects of studying halo stars lies in their intimate connection to one of the greatest mysteries in modern astrophysics: dark matter. While the luminous stars and gas we observe form the visible structure of the Milky Way, they constitute only a small fraction of the galaxy's total mass. The majority of the Milky Way's mass is hidden in the form of dark matter, an elusive, invisible substance that neither emits nor absorbs light but exerts a powerful gravitational influence shaping the galaxy and the cosmos at large. By mapping the motions of halo stars, astronomers unlock critical clues about the distribution, shape, and extent of the Milky Way's dark matter halo, thereby deepening our understanding of the fundamental fabric of the universe. Dark matter was first inferred in the 1930s when astronomers noticed that the visible matter in galaxies could not account for the gravitational forces necessary to keep stars moving at observed speeds, particularly at large distances from the galactic center. In the Milky Way, this discrepancy became especially apparent when studying the rotation curve, the velocity of stars and gas as a function of their distance from the galactic core. Instead of declining with distance as expected from the visible mass, the rotation curve remains flat or even rises, implying a massive, unseen halo of dark matter enveloping the galaxy. The galactic halo, composed of this dark matter, extends well beyond the visible stellar disk, providing the gravitational scaffolding that holds the Milky Way together. However, since dark matter does not interact electromagnetically, it cannot be observed directly with telescopes. Instead, astronomers rely on tracer objects whose motions respond to the galaxy's total gravitational potential. Halo stars, orbiting far beyond the dense galactic disk, serve as ideal tracers. Because halo stars inhabit the outskirts of the Milky Way and follow highly eccentric, often inclined orbits, their velocities and trajectories are sensitive to the gravitational field of the galaxy's dark matter halo. By precisely measuring their positions, velocities, and accelerations, astronomers reconstruct the shape and distribution of dark matter in 3 dimensions. This information is crucial for testing theoretical models of dark matter and galaxy formation. The Gaia Space Telescope, launched in 2013, has revolutionized this field by providing the most precise astrometric measurements to date. Gaia maps the positions, distances, and motions of over 1 billion stars, including many in the halo, allowing astronomers to track their orbits with unprecedented accuracy. Coupled with ground-based spectroscopic surveys that measure radial velocities and chemical compositions, these data sets enable comprehensive dynamical models of the Milky Way's dark matter halo. Studies of halo star motions reveal that the dark matter halo is not perfectly spherical but likely triaxial, or elongated along certain axes. This shape affects how stars orbit and cluster in the halo. For instance, the precession and tidal stripping of stellar streams, remnants of disrupted dwarf galaxies and globular clusters, can only be explained by a dark matter halo with a complex shape and density profile. These stellar streams act like cosmic test particles, their paths bent and stretched by the unseen mass, offering detailed maps of the dark matter's gravitational influence. Furthermore, the mass and extent of the Milky Way's dark matter halo are constrained by halo star dynamics. Estimates place the halo's mass at around 1 trillion solar masses, extending hundreds of thousands of light-years beyond the visible disk. This massive envelope dominates the gravitational environment, influencing not only the Milky Way but also its interactions with neighboring galaxies like Andromeda and the Magellanic Clouds. Understanding the dark matter halo's properties has far-reaching implications. It informs models of how galaxies form and evolve in the cosmic web, how dark matter particles might behave and cluster, and how the Milky Way's structure developed over cosmic time. Moreover, precise knowledge of the dark matter distribution aids in searches for dark matter particles on Earth by predicting regions of higher dark matter density. In addition to global properties, detailed studies of individual halo stars and stellar streams have uncovered substructures in the dark matter halo, such as clumps or subhalos. These features correspond to smaller dark matter concentrations left over from past mergers and accretion events. The presence and properties of these subhalos provide crucial tests for competing dark matter theories, including cold dark matter, warm dark matter, and alternative gravity models. The synergy between halo star kinematics and dark matter research exemplifies the interdisciplinary nature of modern astrophysics. It highlights how observing ancient, faint stars in the outskirts of our galaxy can illuminate the invisible and fundamental components shaping the cosmos. As observational capabilities improve, particularly with future missions like the Nancy Grace Roman Space Telescope and the Vera C. Rubin Observatory, astronomers anticipate even more precise mapping of halo stars and dark matter structures. In summary, halo stars act as luminous beacons navigating the gravitational sea of dark matter enveloping the Milky Way. By charting their motions, astronomers reveal the hidden mass that governs the galaxy's dynamics, structure, and evolution. This connection between the visible and invisible not only advances our understanding of the Milky Way but also probes the fundamental nature of dark matter, the mysterious substance that constitutes the backbone of the universe. Halo stars, ancient suns orbiting far from the vibrant, densely packed spiral arms of the Milky Way's disk, inhabit one of the galaxy's most remote and mysterious regions. They are not only remarkable for their great age and low metallicity, but also for their distance and rarity. Compared to the millions of stars densely concentrated in the galactic disk, including our own Sun, halo stars are comparatively sparse and often located at vast distances from the Earth and the galactic center. Understanding their distribution, scarcity, and remoteness is critical to appreciating the unique role they play in unraveling the history of our galaxy and the universe at large. The galactic disk is a flattened, rotating structure packed with hundreds of billions of stars, interstellar gas, and dust. It is home to the vast majority of stars visible to us in the night sky, many of which are relatively young, metal-rich, and closely packed in spiral arms. The density of stars in the disk near the solar neighborhood is on the order of 0.1 to 1 star per cubic parsec, quite crowded compared to the halo. The disk also includes open star clusters, nebulae, and ongoing star-forming regions, creating a rich, dynamic environment. In stark contrast, the stellar halo is a roughly spherical region extending tens of thousands of light-years above and below the galactic plane. This halo is diffuse and sparsely populated with stars, with densities dropping dramatically as one moves farther from the galactic center. Typical star densities in the halo are on the order of 10 to 10 stars per cubic parsec, making it roughly 10,000 to a million times less dense than the disk. This scarcity arises because the halo primarily consists of old, low-mass stars spread over a huge volume, often moving on extended, eccentric orbits that carry them far from the galactic plane. The vastness and sparseness of the halo make halo stars inherently more difficult to observe and study. Many halo stars lie thousands to tens of thousands of light-years away from Earth. Some are located in the outer halo, extending as far as 100,000 light-years or more from the galactic center, distances that dwarf the roughly 27,000 light-year distance from the Sun to the galactic core. At these immense distances, even intrinsically bright stars appear faint, requiring sensitive telescopes and advanced instruments to detect and analyze them. The rarity and remoteness of halo stars mean that while billions of stars exist within the galactic disk and bulge, only a tiny fraction are halo stars. Estimates suggest that the stellar halo contains about 1% or less of the Milky Way's total stellar mass, with roughly 10 stars spread over an enormous volume. Within this population, only a fraction are accessible for detailed study due to observational limitations. This scarcity contributes to the challenge and excitement of halo star research. Locating these ancient stars requires large-scale, deep sky surveys capable of mapping vast regions of the sky with high sensitivity and precision. Projects like the Sloan Digital Sky Survey (SDSS) and the Gaia mission have revolutionized this field, enabling astronomers to identify halo stars by their unique motions, distances, and chemical signatures, even amidst the overwhelming background of disk stars. Halo stars often reveal themselves through their distinctive kinematics. Their motions differ significantly from those of disk stars. Whereas disk stars move in roughly circular orbits aligned with the galactic plane, halo stars follow highly elliptical and often inclined orbits, frequently passing far above or below the disk. These orbital properties help astronomers distinguish halo stars from the dominant disk population, even when their brightness is low. Additionally, halo stars can be identified by their low metallicity and unique chemical abundance patterns, traits that reflect their ancient origins. These chemical fingerprints differentiate halo stars from the more metal-rich disk stars formed later in the galaxy's history. Spectroscopic surveys enable astronomers to detect these signatures, further refining halo star catalogs. Despite their scarcity, halo stars offer a treasure trove of information about the early Milky Way. Their great distances mean they probe regions of the galaxy that are otherwise inaccessible, providing insights into the galactic potential and the distribution of dark matter. By tracing their orbits, scientists can map the gravitational influence of the galaxy far beyond the luminous disk. The rarity of halo stars also makes them precious targets for understanding stellar evolution and nucleosynthesis in metal-poor environments. Since halo stars are among the oldest observable stars, each one serves as a valuable data point in reconstructing the chemical and dynamical evolution of the galaxy. Discovering extremely metal-poor halo stars has led to breakthroughs in understanding the nature of the first stars and the early enrichment of the interstellar medium. Furthermore, the distances involved mean that studying halo stars often requires observing objects near the limits of current technology. This pushes the boundaries of instrumentation and survey design, driving advances in telescopes, detectors, and data analysis methods. Upcoming facilities like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope promise to expand the census of halo stars dramatically, reaching fainter and more distant populations than ever before. In summary, halo stars are rare and remote wanderers inhabiting the vast, spherical outskirts of the Milky Way. Their scarcity relative to the dense, bustling galactic disk highlights their special status as ancient relics and key tracers of the galaxy's formative years. Despite the challenges posed by their distance and faintness, their study remains central to piecing together the history, structure, and evolution of our galaxy and the broader universe. The light emitted by halo stars carries within it a rich tapestry of information about their chemical compositions, a cosmic barcode etched by the processes of stellar birth, life, and death across billions of years. These chemical signatures, revealed through detailed spectroscopic analysis, are indispensable tools for astronomers seeking to unravel the origins, ages, and histories of these ancient suns. By examining specific element ratios in a halo star's spectrum, scientists can peer into the past, decoding where and when the star formed, the nature of the gas from which it was born, and the astrophysical events that influenced its chemical enrichment. This intricate chemical archaeology forms the cornerstone of modern studies of the Milky Way's halo and the early universe. At the heart of this approach is stellar spectroscopy, the technique of dispersing a star's light into its component wavelengths, its spectrum, and analyzing the absorption lines that appear due to the presence of various elements in the star's atmosphere. Each chemical element leaves a unique set of fingerprints, absorption lines at characteristic wavelengths, allowing astronomers to determine the abundance of elements ranging from hydrogen and helium to heavier metals like iron, carbon, magnesium, and beyond. The relative strength of these lines, and their ratios to one another, provide detailed chemical abundance patterns essential for piecing together a star's history. Halo stars, being predominantly population 2 stars, exhibit chemical compositions distinct from younger, metal-rich population 1 stars found in the galactic disk. One of the defining features of halo stars is their low metallicity, often quantified by the ratio, Fe/H, which compares a star's iron abundance relative to hydrogen against that of the Sun. Many halo stars possess Fe/H values below -1.0, with some extremely metal-poor stars exhibiting values less than -5.0, meaning they have less than 100,000th of the solar iron abundance. Such low metallicity signifies formation from gas that had experienced minimal enrichment from previous generations of stars, marking the star as a relic of the early universe. However, it is not just the overall metal content that matters, but the relative abundances of specific elements. Certain element ratios act as cosmic fingerprints, revealing the nucleosynthetic history of the gas cloud from which the star formed. For example, the ratio of alpha elements, such as oxygen, O, magnesium, Mg, silicon Si, calcium, Ca, and titanium, Ti, to iron, alpha/Fe, is a powerful diagnostic. Alpha elements are primarily produced in massive stars that end their lives as core-collapsed supernovae, while iron is contributed in large amounts by type Ia supernovae arising from older, lower-mass progenitors. Halo stars typically show enhanced alpha/Fe ratios, indicating formation from gas enriched predominantly by massive stars before significant type Ia supernovae contributions. This pattern points to rapid star formation and chemical enrichment early in galactic history. Another revealing chemical ratio involves carbon and nitrogen abundances. Carbon-enhanced metalpoor (CMP) stars are a special class of halo stars exhibiting unusually high carbon relative to iron. Their origin is linked to nucleosynthetic processes in the first generations of stars and binary interactions such as mass transfer from an asymptotic giant branch (AGB) companion. Studying the prevalence and properties of CMP stars sheds light on the diversity of early stellar populations and the complexity of chemical enrichment. The ratios of heavier neutron capture elements, produced via the slow S process or rapid R process, neutron capture in certain supernovae or neutron star mergers, provide further clues. Measuring elements like barium, Ba, europium, Eu, and strontium, Sr, informs astronomers about the astrophysical sites and timescales of element formation in the early Milky Way. Some halo stars show enhancements in R process elements, suggesting enrichment by rare but highly energetic events. Additionally, the abundance patterns of odd Z elements such as sodium, Na, aluminum, Al, and potassium, K, contribute to the chemical fingerprint. Variations in these elements can indicate pollution from specific nucleosynthetic pathways or progenitor mass ranges, helping to distinguish between stars formed in different environments or progenitor systems. By comparing observed chemical signatures with theoretical nucleosynthesis models, astronomers reconstruct the star formation histories of the halo and its progenitor galaxies. Different dwarf galaxies and stellar clusters have distinct chemical evolution tracks, reflected in the element ratios of their stars. This allows identification of accreted halo stars originally formed in satellite galaxies versus those formed in situ within the Milky Way. One remarkable application is the identification of stars linked to known accretion events, such as the Gaia Enceladus or Sausage merger. Stars belonging to this ancient dwarf galaxy remnant exhibit coherent chemical signatures and orbital properties that distinguish them from native Milky Way halo stars. This chemical tagging enables astronomers to disentangle the complex assembly history of the halo, associating groups of stars with their original birth environments. Chemical abundances also serve as chronometers, helping estimate stellar ages. Certain element ratios, such as those involving radioactive isotopes like thorium and uranium relative to stable elements, provide nuclear cosmochronology clocks. Measuring these ratios in halo stars allows age determinations independent of stellar evolution models, adding robustness to our understanding of the timeline of the early universe. Moreover, the chemical signatures offer clues about the nature of the first stars. By matching abundance patterns of extremely metal-poor halo stars to yields predicted from population 3 supernova models, astronomers infer properties like progenitor masses and explosion energies. This indirect method is crucial given the observational challenge of detecting population 3 stars directly. The advent of large-scale spectroscopic surveys, such as the Apache Point Observatory Galactic Evolution Experiment, APOGEE, and the Galactic Archaeology with Hermes, Gala, survey, alongside Gaia's astrometric data, has ushered in a new era of chemical cartography. These surveys have dramatically expanded the sample of halo stars with detailed chemical information, enabling statistical analyses of the halo's chemical substructure and gradients. Despite these advances, challenges remain. Precise abundance determinations require high-resolution spectroscopy and careful modeling of stellar atmospheres, especially for cool, metal-poor stars where non-local thermodynamic equilibrium effects and three-dimensional modeling become important. Furthermore, interpreting chemical signatures demands sophisticated chemical evolution models that account for complex processes like gas inflows, outflows, star formation bursts, and mergers. Nevertheless, the chemical signatures imprinted in halo stars stand as some of the most powerful tools for exploring the Milky Way's past. They provide a multidimensional dataset, combining chemistry, kinematics, and age, that allows astronomers to piece together a detailed narrative of galactic formation and evolution. From identifying ancient merger remnants to tracing the fingerprints of the first stars, these chemical clues help transform halo stars from distant curiosities into vital witnesses of cosmic history. In essence, the spectrum of a halo star is not merely light but a coded message from the dawn of time, revealing the birthplaces and journeys of some of the oldest stellar inhabitants of our galaxy. Through patient observation and meticulous analysis, astronomers continue to decode this message, enriching our understanding of the cosmos and our place within it. The term, Cosmic Dawn, evokes a poetic yet profound epoch in the history of the universe, an era when the first luminous structures ignited and the cosmos transitioned from darkness into light. It was during this transformative period, roughly between 200 million and 1 billion years after the Big Bang, that the earliest stars and galaxies began to form, illuminating the vast cosmic landscape for the first time. In many ways, the ancient halo stars that still drift in the Milky Way's extended halo are direct messengers from this cosmic dawn, stellar relics that bear witness to those first light-filled moments, and the processes that shaped the universe's early evolution. To truly appreciate halo stars as relics of the cosmic dawn, it's important to contextualize what this epoch represents. Prior to cosmic dawn, the universe was a dark, cold expanse filled primarily with neutral hydrogen and helium gas. Following the recombination era, around 380,000 years after the Big Bang, the universe had cooled enough for protons and electrons to combine into neutral atoms, leading to a largely opaque, featureless, dark age. During this period, no stars or galaxies existed to shine or sculpt the cosmic environment. It was a time of cosmic stillness, with only the faint afterglow of the cosmic microwave background as a whisper of light. Cosmic dawn marks the end of this darkness, initiated by the formation of the first generation of stars, population 3 stars, within small dark matter halos that had begun to gravitationally collapse. These stars were massive, hot, and short-lived, and they forged the first heavy elements through nuclear fusion, ultimately exploding as supernovae and seeding the surrounding medium with the ingredients necessary for subsequent generations of stars and galaxies. The light from these first stars began to reionize the universe, splitting hydrogen atoms back into protons and electrons and transforming the intergalactic medium from neutral to ionized. This epoch of reionization effectively lifted the cosmic fog, enabling light to travel freely and ushering in the transparent universe we observe today. Halo stars are the tangible, long-lived survivors of this era of first light. While the massive population 3 stars themselves burned out quickly and are no longer observable, their descendants, the low-mass, second-generation stars, formed from gas clouds enriched by the first star's nucleosynthesis. These second-generation stars, many of which reside today in the galactic halo, embody the chemical and dynamical signatures of that primordial time. Their extremely low metallicities and distinctive elemental abundance patterns serve as fingerprints of the early chemical enrichment and star formation events. As relics of cosmic dawn, halo stars carry unparalleled insights into the processes that governed the birth of galaxies and the early universe's structure formation. Their ages, often exceeding 13 billion years, place them as some of the oldest observable objects in the cosmos. They are natural laboratories for testing theories of early star formation, feedback, and chemical evolution. For instance, the variations in metallicity among halo stars reflect the patchy and gradual enrichment of the interstellar medium during cosmic dawn, as early supernovae distributed heavy elements unevenly across nascent galaxies. In addition to chemical evidence, the kinematics and spatial distribution of halo stars offer clues about the hierarchical nature of galaxy formation. The cosmic dawn was a time of intense merging and accretion, when small proto-galaxies and dark matter halos coalesced to form larger structures. Many halo stars were likely born in these smaller systems before being incorporated into the Milky Way through gravitational interactions. Thus, they preserve the memory of the galaxy's assembly, acting as fossilized remnants of these primordial building blocks. Observations of halo stars also complement the study of high-redshift galaxies and quasars, objects observed at great distances whose light has traveled billions of years to reach us. While telescopes like the James Webb Space Telescope, JWST, peer directly into the cosmic dawn by capturing the faint glow of early galaxies, halo stars offer a closer, more detailed record of the same epoch's physical and chemical conditions. Their proximity allows for precise spectroscopic analysis, revealing elemental abundances and isotopic ratios impossible to measure in distant galaxies. Furthermore, halo stars help illuminate the timeline and duration of the cosmic dawn and reionization. By comparing the ages and metallicities of different halo stars, astronomers infer the pace at which early star formation and chemical enrichment unfolded. Some halo stars formed rapidly after the first supernovae enriched their environments, while others emerged later as more massive galaxies took shape. This temporal layering provides a nuanced picture of how the universe transitioned from simplicity to complexity. Beyond their scientific value, halo stars evoke a profound philosophical perspective. They are cosmic time travelers, their photons traversing the vastness of space and epochs of time to reach us. In a sense, each halo star is a living monument to the universe's earliest chapters, a direct link connecting humanity to the dawn of starlight, to the very beginnings of cosmic structure, and to the processes that ultimately led to our existence. The story told by halo stars is one of endurance, transformation, and cosmic continuity. They remind us that the universe is not static but a dynamic tapestry woven from billions of years of evolution, merging the ancient past with the present. These stars, born when the universe was young and unfamiliar, still shine today, bridging the gulf between the primal cosmic dawn and the intricate galaxy we call home. Looking forward, future astronomical missions promise to deepen our understanding of halo stars as relics of cosmic dawn. The upcoming Nancy Grace Roman Space Telescope, for example, will enable deep infrared surveys capable of uncovering even fainter and more distant halo star populations. Combined with advances in spectroscopic technology and computational modeling, this will refine our knowledge of the earliest star formation epochs and the role halo stars play in preserving that history. In essence, halo stars are more than mere points of light in the night sky. They are messengers from the cosmic dawn, illuminating the universe's first steps toward complexity and life. By studying these ancient suns, we engage with a cosmic narrative spanning billions of years, connecting the infancy of the cosmos to our present moment, and inspiring awe at the vast, unfolding story of existence. When astronomers talk about halo stars, they are often referring to one of the most important categories of ancient stellar populations in the galaxy, stars that are so old, their light began shining not long after the universe itself was born. But while they all inhabit the same extended, spherical halo surrounding the Milky Way, not all halo stars share the same birthplace. Some formed right here, deep within the gravitational well of our own galaxy, while others are cosmic immigrants, born in entirely different galaxies before their homes were torn apart and absorbed by the Milky Way's gravity. These two categories, accreted and in-situ, represent fundamentally different origins, and untangling their histories has been one of the major goals of galactic archaeology. The difference is not just a matter of where they were born, it's about the conditions under which they formed, the kinds of chemical elements they contain, the shapes and orientations of their orbits, and what these factors reveal about the turbulent process of galaxy building. An in-situ halo star is essentially a native Milky Way citizen. These stars formed when the proto-Milky Way was just beginning to take shape, over 12 billion years ago, during an era when the galaxy was more of a loosely bound cloud of gas and dark matter than a structured spiral. In those early days, vast reservoirs of pristine gas, composed almost entirely of hydrogen and helium from the Big Bang, collapsed under gravity and began forming the very first generations of stars in our galaxy's core and extended halo. Some of these early star-forming regions were chaotic, with supernova explosions rapidly enriching the surrounding gas with heavier elements, and new stars forming almost immediately from that enriched material. This process gave in-situ halo stars a specific chemical signature. While they are metal-poor compared to the Sun, they tend to be richer in certain alpha elements, like oxygen, magnesium, and silicon, than stars that came from outside the Milky Way. That pattern points to rapid star formation driven by massive stars, whose short lives end in violent Type II supernovae, which are prolific producers of alpha elements. The high alpha-to-iron ratios of these stars are essentially a fingerprint of a fast, intense starburst history. Accreted halo stars, on the other hand, have a much more nomadic backstory. They began their lives far from the Milky Way, in small satellite galaxies that were quietly orbiting the cosmic void. These dwarf galaxies evolved at a much slower pace than the Milky Way, forming stars over longer timescales and with less intense bursts of activity. As a result, their stars tend to have different chemical abundances, especially lower alpha-to-iron ratios, because the slower pace of star formation allowed a larger influence from Type I supernovae, which produce more iron relative to alpha elements. This is one of the primary ways astronomers can tell that a star was born elsewhere. If its chemical fingerprint doesn't match the rapid enrichment history of the early Milky Way, it likely came from a galaxy that evolved under a different timeline. The story of how these accreted stars came to live in the Milky Way is one of cosmic violence and inevitability. The universe builds large galaxies by having them swallow smaller ones, a process called hierarchical assembly. Over billions of years, the Milky Way's gravity pulled in countless dwarf galaxies, stripping away their stars, gas, and dark matter. These stripped stars, now unbound from their original homes, were flung into long, looping orbits that eventually mixed into the halo. Sometimes the remnants of these mergers are still visible today as stellar streams, long, ribbon-like trails of stars that mark the former paths of the devoured galaxies. One of the most famous examples of such an event is the Gaia-Enceladus merger, which occurred around 8 to 10 billion years ago. This was a collision between the young Milky Way and a dwarf galaxy roughly a quarter of its mass, and it contributed a massive population of stars to the halo, many of which have distinctive retrograde orbits, meaning they move around the galaxy in the opposite direction from the Milky Way's disk rotation. Orbital dynamics are another important clue for distinguishing in-situ from accreted halo stars. In-situ stars, having formed deep within the gravitational well of the proto-Milky Way, tend to have more bound, less extreme orbits, often staying relatively close to the galactic center. Many of them move in the same general direction as the Milky Way's disk rotation, even if their orbits are more elliptical and inclined. Accreted stars, however, can be found on far more eccentric and inclined trajectories, including retrograde paths. These irregular orbits reflect the fact that the stars were deposited into the halo during the random and chaotic infall of their parent galaxies, which could have been moving in any direction relative to the Milky Way at the time of merger. The spatial distribution of these two populations is also telling. In-situ halo stars are more concentrated toward the inner halo, closer to the galactic center, while accreted stars are more common in the outer halo, where the gravitational mixing from mergers has been less complete. This pattern fits with the idea that the Milky Way's first stars formed in its densest, central regions, and only later did external stars get scattered across the more remote halo regions. However, the boundary between inner and outer halo is not a hard line, and over billions of years, dynamical processes have blurred the distinction to some extent, making detailed chemical and kinematic studies essential to teasing the two populations apart. It's also important to note that these populations don't just differ in where they came from, they tell different chapters of the Milky Way's history. In-situ halo stars are direct witnesses to the galaxy's earliest, most violent period of internal star formation, when the Milky Way was still assembling its own structure and identity. They record the conditions of the young galaxy's interstellar medium, the types of supernovae that dominated its chemical enrichment, and the speed with which those first generations of stars lived and died. Accreted stars, by contrast, are historical imports, They tell the story of the Milky Way's interactions with its neighbors, the galaxies it absorbed, and the pace and scale of those mergers. Together, the two populations form a dual narrative, one local, one cosmopolitan, that reveals the Milky Way's growth from a small proto-galaxy to the massive spiral we see today. The tools astronomers use to tell these stories are a combination of large-scale stellar surveys, precise astrometric measurements from missions like ESA's Gaia, and high-resolution spectroscopy from ground-based telescopes. Gaia, in particular, has revolutionized this field by providing the positions, distances, and motions of more than 1 billion stars, allowing researchers to map the halo in unprecedented detail and link chemical information with orbital dynamics. By combining chemistry and motion, astronomers can tag stars to specific merger events or identify those that likely formed in situ. This synergy has allowed the reconstruction of major events like the Gaia-Enceladus merger and even smaller, more recent accretion events, some of which may still be ongoing with the Milky Way's surviving dwarf galaxy companions, like the Sagittarius dwarf spheroidal galaxy. What's remarkable is how the differences between accreted and in-situ halo stars survive over such vast timescales. Even after billions of years of gravitational interactions, dynamical heating, and orbital mixing, the chemical signatures imprinted at birth remain, acting like a stellar DNA test that reveals a star's true origins. This persistence means that by carefully analyzing the halo stars, astronomers can essentially perform galactic genealogy, tracing each star back to its birthplace, whether it was here or far away. Some halo stars are not just old, they are effectively immortal on cosmic timescales. These are typically the smallest, coolest, and faintest stars, low-mass red dwarfs. While massive stars burn through their fuel in a few million years, low-mass stars sip it slowly, stretching their lives out to trillions of years, far beyond the current age of the universe. The universe today is about 13.8 billion years old, yet the smallest red dwarfs can live for more than 10 trillion years, possibly even up to 15 trillion in extreme cases. To put that in perspective, these stars could still be shining when galaxies have long since stopped forming new stars and the universe has entered what astronomers call the degenerate era, a future epoch where only stellar remnants and long-lived red dwarfs remain. This extreme longevity comes down to the physics of nuclear fusion. In a star like the Sun, the energy comes from fusing hydrogen into helium in the core, but the intense pressure and temperature make this process happen at a furious rate. In a red dwarf, the pressure and temperature are lower, and the fusion process is slower and more stable. Instead of rushing through their fuel supply, red dwarfs pace themselves, burning hydrogen so slowly that they can last hundreds or thousands of times longer than the Sun. Another key factor is that red dwarfs are fully convective, meaning the material in the star circulates from the core to the surface and back again. This mixing ensures that nearly all the hydrogen in the star is eventually available for fusion, unlike in larger stars where much of the hydrogen remains locked away and unused. It's like a candle that can melt and burn every last bit of wax instead of leaving unused chunks behind. Because of this, a red dwarf that formed shortly after the Big Bang could still be in the earliest stages of its life today. In fact, astronomers suspect that some of the halo's oldest red dwarfs haven't even reached the midpoint of their lifespan. If left undisturbed, they will continue shining quietly for trillions of years into the future. That means that, in a way, some halo stars are not just relics of the past but also ambassadors to the far future of the cosmos. They connect the first chapters of the universe's story with its distant, twilight years. This longevity has profound implications for the future evolution of the Milky Way and the larger universe. When all the brighter, more massive stars have burned out, these tiny halo red dwarfs will still be emitting faint, steady light, keeping some parts of the galaxy illuminated even after everything else has gone dark. In the era when the cosmic background radiation has faded to near absolute zero and black holes have begun to evaporate through Hawking radiation, the last vestiges of starlight in the universe will likely come from stars like these. And since some of them were born in the halo's earliest days, their lifetimes span not just the current age of the cosmos but many multiples of it. What's fascinating is that this kind of star is incredibly stable. Red dwarfs are resistant to many of the instabilities that plague larger stars. They don't go supernova, they don't pulsate wildly, and they don't shed large amounts of mass. Instead, they live quiet, predictable lives. If a red dwarf is left alone in the halo, far from the crowded regions of the galactic disk where collisions and close encounters are more likely, it has an excellent chance of surviving until the universe itself changes so dramatically that stars can no longer exist in any recognizable form. It's worth noting that humans have never seen a red dwarf complete its life cycle. The universe simply hasn't been around long enough for even the smallest and slowest burning stars to reach the end. Theoretical models of stellar evolution give us confidence in their projected lifetimes, but in reality, every single red dwarf that has ever formed is still burning today. This makes halo red dwarfs an ongoing experiment in cosmic patience, objects that formed from the universe's primordial gases, settled into slow fusion, and will continue to exist long after Earth, the Sun, and the Milky Way's current structure have vanished. In addition, because halo stars are often far from the busy, disruptive regions of the galaxy, they are more likely to survive for their full theoretical lifetimes. Stars in the dense galactic disk might eventually be perturbed, collide, or be pulled into strange orbits that affect their stability. But in the vast, low-density halo, space is so empty that a star can drift for billions of years without ever coming close to another star. This isolation acts like a cosmic safe zone, allowing them to continue burning peacefully in the background while the rest of the universe evolves around them. The combination of low mass, slow fusion, and isolation means that some halo stars could potentially survive until the very end of the stelliferous era, the current age of star formation, which will eventually give way to an era where no new stars are born. In that distant time, the universe will be lit only by the dim glow of ancient red dwarfs and the occasional flare from dying white dwarfs or neutron stars merging. Eventually, even these red dwarfs will run out of fuel, transitioning into cold, inert stellar remnants called black dwarfs. But that's a fate so far in the future that it defies human comprehension. Tens of trillions of years from now, long after our galaxy has merged with Andromeda and after countless cosmic events have reshaped the universe. From a human perspective, the endurance of these stars is almost philosophical. They are the ultimate survivors, outlasting civilizations, planets, and even galaxies as we know them. If intelligent life exists somewhere else in the galaxy, billions of years from now, it's possible that their night skies will still include some of the same halo red dwarfs we can see today. These stars are silent witnesses to the birth of the cosmos, the growth of galaxies, and the slow, inevitable march toward a darker, colder universe. In a way, halo stars with such extreme longevity give us an anchor in the incomprehensible vastness of time. While our own sun will one day expand, engulfing Mercury and Venus before ending its life as a white dwarf, some of these tiny, ancient stars will continue shining, faint but steadfast, through eons that make even geological time look fleeting. They are not just old stars. They are cosmic timekeepers, counting down an age of light that will last longer than the universe has yet existed. And in the halo, drifting in lonely orbits far above and below the galaxy, they will watch the slow transformation of the cosmos with the patience only a star could have. Finding and studying halo stars is a bit like trying to identify ancient, scattered artifacts across an entire continent, except the continent is the three-dimensional structure of the Milky Way, and the artifacts are so faint and so far away that they can be easily lost in the glare of younger, brighter stars. Astronomers have spent decades refining the tools and methods needed to pick out these elusive stellar relics from the billions of other stars in the galaxy. The effort requires not only some of the most powerful telescopes on Earth and in space, but also highly sophisticated surveys and missions designed to measure positions, motions, and spectra with exquisite precision. One of the most groundbreaking tools for studying halo stars is the European Space Agency's Gaia mission. Launched in 2013, Gaia has revolutionized our understanding of the Milky Way's structure by mapping the positions and motions of over 1 billion stars. Unlike earlier missions that might have focused on brightness and general location, Gaia's key achievement is in its astrometric precision, the ability to pinpoint a star's position in the sky to within microarc seconds and then track how it moves over time. For halo stars, this is vital. Many of them have orbits that carry them far above and below the galactic plane, and these orbital paths can reveal whether a star likely formed in the Milky Way or was captured from another galaxy. Gaia's data allows astronomers to reconstruct these trajectories in 3 dimensions, essentially giving a time-lapse of stellar motions over millions of years. Gaia's measurements are complemented by large-scale ground-based surveys like the Sloan Digital Sky Survey (SDSS), which began in the early 2000s and has since cataloged millions of stars and galaxies with detailed spectral information. Spectroscopy is critical for halo star research because it reveals the chemical fingerprints embedded in starlight, the abundance of elements like iron, magnesium, and carbon. These patterns tell astronomers about a star's age, the kind of environment it formed in, and whether it might have originated in a different galaxy. For example, a halo star with an unusual ratio of magnesium to iron might be traced back to a small dwarf galaxy that was swallowed by the Milky Way billions of years ago. Combining SDSS spectra with Gaia's motion data has been one of the most fruitful approaches in recent years, uncovering entire populations of stars that were once part of other galaxies. In addition to SDSS, other spectroscopic surveys like Apogee, Apache Point Observatory Galactic Evolution Experiment, and LAMOS, Large Sky Area Multi-Object Fiber Spectroscopic Telescope, play crucial roles. Apogee, for example, operates in the infrared, allowing it to peer through dust and study stars that might otherwise be hidden from optical telescopes. While many halo stars are found in relatively dust-free regions, having a complete survey of stars in different environments helps create a more accurate map of the Milky Way's full structure. LAMOS, with its ability to collect spectra from thousands of stars in a single night, provides an enormous amount of data that helps identify rare, extremely metal-poor stars, exactly the kind of ancient stars scientists are most interested in. Space-based observatories beyond Gaia also contribute. The Hubble Space Telescope, despite being more than 3 decades old, continues to provide some of the sharpest images available, which can be used to identify faint halo stars and measure their properties. Hubble's ultraviolet capabilities have been particularly useful for detecting certain chemical elements that are harder to observe from the ground due to Earth's atmosphere. Similarly, upcoming missions like the Nancy Grace Roman Space Telescope will add even greater surveying power, with wide-field infrared imaging that can help map the outer halo in unprecedented detail. Radio astronomy has also been surprisingly useful in studying halo structures, not by detecting the stars themselves, but by mapping the neutral hydrogen gas associated with small galaxies and streams in the halo. Facilities like the Green Bank Telescope and the Australian Square Kilometre Array Pathfinder, a SCAP, can detect the faint gas trails left behind when dwarf galaxies are torn apart by the Milky Way's gravity. These trails often lead astronomers to the stellar debris, helping them identify populations of halo stars that match the disrupted system. Another essential category of tools is numerical simulation. While not telescopes in the traditional sense, computer models allow astronomers to test different scenarios for halo formation and compare them with observational data. Simulations from projects like Illustris-TNG or EAGLE can reproduce large-scale galaxy assembly processes and predict the kinds of stellar orbits and chemical signatures we should see if the Milky Way formed in a particular way. Then, by comparing these predictions with data from Gaia, SDSS, and Apogee, astronomers can refine their theories and even design new observational campaigns to target specific halo regions. Surveys that focus on variable stars, like those conducted by the OGLE Optical Gravitational Lensing Experiment and ZTF Zwicky Transit Facility, also help. Certain types of variable stars, such as our Lyrae, are excellent tracers of the halo because they are both ancient and relatively easy to identify from their light curves. Once located, these stars can serve as markers for mapping the halo's extent and structure, especially in regions where halo stars are sparse. The coordination between these tools is what makes the modern study of halo stars possible. Gaia might flag a star with unusual motion, SDSS might then confirm it has extremely low metallicity, Apogee could reveal its detailed elemental composition, and Hubble could provide precise distance measurements. Together, these data points create a complete picture, transforming what would otherwise be a faint, unremarkable point of light into a well-characterized relic of the early universe. What's remarkable is that even with all these tools, we're still only scratching the surface. The halo extends far beyond the easily visible parts of the Milky Way, and its most distant members are so faint that they challenge even our best telescopes. Future instruments, such as the extremely large telescope, ELT, in Chile, will push the limits of resolution and light-gathering power, allowing astronomers to study halo stars in far greater detail. Likewise, the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will provide an unprecedented decade-long record of stellar motions and variability, which will be invaluable for tracking halo stars over time. The study of halo stars is a testament to how far astronomy has advanced, from early observations that could barely distinguish them from disk stars, to today's multi-instrument, multi-wavelength, multi-decade campaigns that treat each star as a key piece of cosmic history. Every new dataset doesn't just add to our catalog. It refines our understanding of how the Milky Way grew from a collection of smaller systems into the grand spiral we see today. In this sense, the tools of discovery are not just instruments, they're time machines, allowing us to peer into the galaxy's deep past and uncover the stories of stars that have been wandering the halo for more than 13 billion years. Astronomers have long thought they had a fairly good understanding of what halo stars should be like: ancient, metallic, slow-burning relics moving in wide and often chaotic orbits far above and below the galactic plane. But as is often the case in astronomy, the universe has a habit of surprising us. When researchers began mapping and studying the halo in unprecedented detail, they found stars that broke the expected patterns, cosmic oddballs whose very existence challenged long-held assumptions about galactic history. These unexpected finds have become some of the most intriguing pieces of the puzzle, hinting at events and processes that astronomers had not previously considered or had only theorized without evidence. One of the most striking surprises has been the discovery of halo stars with unusual chemical fingerprints. Most halo stars, as we've discussed before, are incredibly metallic, meaning they have very low concentrations of elements heavier than hydrogen and helium. This is because they formed early in the universe, before successive generations of supernovae had time to seed the cosmos with heavier elements. Yet, scattered throughout the halo, astronomers have detected stars whose spectra show unexpectedly high levels of certain metals or strange elemental ratios that don't match any typical enrichment pathway. For example, some halo stars contain an unusually high abundance of carbon, making them carbon-enhanced metallic (CMP) stars. These stars are particularly fascinating because their chemical patterns suggest that they may have been enriched by the very first supernovae, possibly from the explosions of massive population 3 stars, stars so massive and short-lived that they've never been directly observed. Even more puzzling are halo stars that show evidence of elements like europium or barium in quantities that seem incompatible with the environment in which they likely formed. These heavy elements are generally produced by rare, exotic events, such as neutron star mergers or certain types of supernovae known as R-process events. Finding them in an otherwise primitive star means that the material from which the star formed must have been touched by such an event extremely early in the galaxy's history. This hints at a more chaotic and violent early Milky Way than we once thought, where rare but powerful cosmic explosions could leave indelible chemical signatures on isolated stars that would wander the halo for billions of years. Some of the most surprising chemical fingerprints belong to stars that seem to have been born far from the Milky Way entirely. Their elemental ratios do not match those of stars from our galaxy, instead resembling the patterns seen in stars of dwarf galaxies. This reinforces the theory that the halo is a graveyard of cannibalized systems, the remnants of small galaxies that the Milky Way devoured over cosmic time. When astronomers spot such stars, they're not just finding a peculiar chemical makeup. They're holding in their data the last surviving piece of a galaxy that no longer exists as a separate entity. These stars are living fossils of ancient mergers, offering a direct connection to the Milky Way's cannibalistic past. Chemical anomalies aren't the only source of surprise. The motions of some halo stars have also defied expectations. Thanks to missions like Gaia, which precisely tracks the positions and velocities of over 1 billion stars, astronomers have been able to reconstruct the orbits of halo stars in 3 dimensions. In doing so, they've uncovered stars with movement patterns that suggest truly unusual histories. For instance, while most halo stars follow elongated, eccentric orbits around the galaxy, some have been found moving at speeds so high that they're barely gravitationally bound, or in some cases, not bound at all. These so-called hypervelocity stars are rare, but their presence in the halo suggests dramatic origins, possibly involving gravitational slingshots from interactions with the supermassive black hole at the galaxy's center, or ejections caused by close encounters in dense stellar clusters. In other cases, astronomers have found halo stars whose orbits seem to align with large, coherent streams of stars, remnants of disrupted dwarf galaxies or globular clusters. These stellar streams are like breadcrumb trails across the sky, marking the paths of long-vanished systems as they were torn apart by the Milky Way's gravity. Finding a halo star in one of these streams is like catching a lone survivor still walking the road their galaxy once traveled. But some stars don't fit any known stream or merger event, suggesting that the halo's history includes smaller, forgotten accretion episodes or interactions with objects that have since been completely assimilated. Another unexpected category involves stars that are both old and surprisingly metal-rich, a combination that challenges the neat correlation between age and metallicity. Such stars might have formed in environments where metal enrichment happened unusually quickly, perhaps in the dense cores of small galaxies before they were captured by the Milky Way. Their presence forces astronomers to refine their models of chemical evolution and galactic assembly, acknowledging that the universe's history is more patchwork and uneven than a simple timeline would suggest. Occasionally, the surprises in the halo are less about single stars and more about larger structures. For example, Gaia data has revealed vast, previously unknown components of the halo, such as the Gaia Enceladus/Sausage Remnant, the fossil record of a major galactic merger that took place billions of years ago. The stars from this event share similar orbits and chemical compositions, but they were hiding in plain sight until precise motion data revealed their common origin. This finding alone dramatically reshaped our understanding of how the Milky Way grew to its current size. What makes these unexpected discoveries so important is that they act like cracks in the smooth facade of our galactic history. Each anomaly is a reminder that our galaxy's past wasn't a simple, orderly progression from early collapse to present structure, but rather a chaotic blend of mergers, collisions, starbursts, and unique enrichment events. Halo stars, especially the oddballs, are crucial to reconstructing this history because they've spent most of their lives in the relatively quiet outskirts of the galaxy, preserving the chemical and dynamical fingerprints of their birth environments. While stars in the disk have been stirred and mixed over billions of years, halo stars often carry clearer, more pristine evidence of the conditions under which they formed. The ongoing surprise factor in halo star research is also a testament to the power of modern astronomical tools. Missions like Gaia, combined with massive spectroscopic surveys such as Apogee, LAMOST, and Gaia, are allowing astronomers to collect data on millions of stars at a level of detail unimaginable a generation ago. This flood of data means that unusual stars, which once might have gone unnoticed in small samples, now stand out clearly. As datasets grow, so too does the likelihood of finding stars that defy current models. And each of these stars has the potential to rewrite a small but important part of the Milky Way's origin story. In the end, the unexpected finds in the galactic halo are far more than astronomical curiosities. They are direct evidence that the Milky Way's history is still being uncovered and that the early universe was richer, stranger, and more dynamic than we have yet fully imagined. Every unusual chemical fingerprint, every oddball orbit, and every hypervelocity outlier is another piece of a cosmic jigsaw puzzle that, when assembled, will reveal the true, messy, and fascinating story of how our galaxy came to be. And given how vast and sparsely explored the halo remains, it's almost certain that more surprises are waiting, perhaps ones that will challenge not just our ideas about the Milky Way, but about galaxy formation and evolution throughout the universe. When astronomers first began piecing together the idea of the Milky Way's halo, it was natural to wonder whether our galaxy was unique in having such a vast, faintly populated outer sphere of ancient stars and globular clusters. As telescopes improved and imaging techniques became more refined, it became clear that halos are not a peculiar feature of the Milky Way at all. They are a common, perhaps even universal, component of large galaxies. The ability to study halo stars in other galaxies, particularly in our galactic neighbor Andromeda, M31, has opened a whole new chapter in understanding not only the Milky Way's own origins, but also the broader history of galaxy formation across the universe. The comparison between halos is one of the most powerful tools astronomers have for figuring out what events are typical, and which are unique quirks of our galaxy's past. The Andromeda Galaxy is by far the most useful target for such comparisons. It is close enough, just over 2.5 million light-years away, that modern telescopes can resolve many of its individual stars, especially in the outskirts where the density is low and the background clutter is minimal. Using instruments like the Hubble Space Telescope and more recently, the James Webb Space Telescope, JWST, astronomers can pick out faint, ancient stars in Andromeda's halo with enough detail to measure their brightness, colors, and sometimes even their chemical fingerprints. This level of detail allows for direct comparison to halo stars in the Milky Way, revealing both surprising similarities and intriguing differences. One of the first major surprises in these comparisons came when astronomers realized that Andromeda's halo seems to be more massive and more extended than the Milky Way's. In fact, studies suggest that Andromeda's stellar halo stretches out over 1.3 million light-years in diameter, more than twice the size of our galaxy's halo. This is not just a matter of scale. A bigger halo often means a more tumultuous history of galaxy mergers and accretions. Andromeda appears to have undergone more frequent or more massive collisions with other galaxies in the relatively recent past, astronomically speaking, which would explain why its halo contains more stars, streams, and substructures compared to the smoother, more diffuse Milky Way halo. In Andromeda's halo, astronomers have detected vast stellar streams, long, curving ribbons of stars that trace the remnants of devoured galaxies. These streams are far more prominent and numerous than those we see around the Milky Way, hinting at the possibility that Andromeda's history is more violent. For example, the giant stellar stream in Andromeda is thought to be the shredded remains of a galaxy about one-third the mass of the Milky Way's Large Magellanic Cloud. This debris, stretching across more than 120,000 light-years, is an unambiguous sign of a major galactic feast in Andromeda's past. The chemical makeup of halo stars in Andromeda also tells a compelling story. When astronomers measure the metallicity, the abundance of elements heavier than hydrogen and helium, they find that Andromeda's halo stars are, on average, slightly richer in metals than those in the Milky Way's halo. This suggests that Andromeda's halo-building mergers may have involved galaxies that had already gone through more star formation and chemical enrichment, producing stars with more complex compositions. This detail matters because it hints at differences in the timing and nature of halo assembly between the two galaxies. If Andromeda's mergers were, on average, more recent, they would have pulled in galaxies that had more time to produce heavier elements before being consumed. Interestingly, these differences extend beyond just the number and composition of halo stars. Observations show that Andromeda's halo is more asymmetric, with certain regions more densely populated than others. In the Milky Way, the halo is somewhat lopsided too, but Andromeda's imbalance is more pronounced. This could mean that some of its most significant merger events happened relatively recently, and the system has not yet had time to fully mix and smooth out. The ongoing asymmetry serves as a living snapshot of galactic cannibalism in progress, allowing astronomers to study the merging process in a way that our older, more settled halo does not easily allow. Andromeda is not the only galaxy where halo stars can be studied, although it is the most detailed example. Other nearby galaxies in the local group, such as Triangulum, M33, the Large and Small Magellanic Clouds, and even dwarf spheroidal galaxies like Sculptor and Fornax, also possess halos, though their smaller size and lower luminosity make them trickier to investigate. Nonetheless, modern surveys and deep imaging projects like the Pan-Andromeda Archaeological Survey, PANDAS, and the Subaru Telescope's Hyper-SuprimeCam have begun mapping halo stars in these galaxies with remarkable precision. The more galaxies we compare, the better we can tell whether features like metal-rich halos, giant streams, and asymmetries are common products of galactic evolution or special quirks of individual histories. Even galaxies outside the local group are becoming accessible for halo studies thanks to advances in both ground-based and space-based observing. While it is impossible to pick out individual halo stars in galaxies tens of millions of light-years away, astronomers can detect the integrated light from these faint outer regions and analyze it to estimate average ages, metallicities, and stellar densities. Massive elliptical galaxies, for example, have halos too, though their formation stories differ from spiral galaxies like the Milky Way and Andromeda. The halos of ellipticals are often even larger in proportion to the galaxy itself, and may hold clues about how galaxy mergers and dense clusters differ from the more isolated environments of spirals. Comparing halos across multiple galaxies has another important consequence. It provides a test for cosmological models. In the standard lambda cold dark matter model, galaxies grow hierarchically, starting from small clumps that merge into larger and larger systems. The outer halo is a fossil record of this process, and simulations predict specific patterns of metallicity gradients, substructure, and stellar motion depending on the merger history. If observations of halos in the real universe, especially in other galaxies, match these predictions, it strengthens the model. If not, it forces astronomers to rethink key assumptions about how galaxies assemble. The Milky Way and Andromeda will one day provide an especially interesting before and after view of halo evolution. In roughly 4 billion years, the two galaxies are expected to collide and merge into a single, larger elliptical galaxy. When this happens, their halos will blend, distort, and eventually form a new, even more extended halo. Studying each galaxy's halo now gives astronomers a baseline to compare against the aftermath of the merger. Although no human observer will be around to see it firsthand, our records and simulations will make it possible for future astronomers, or whoever's watching the skies then, to piece together the transformation. In essence, studying halo stars in other galaxies is like being able to check another person's family album to see how their history compares to yours. While every galaxy's halo tells a slightly different story, the overall similarities confirm that halos are universal features of galactic structure, while the differences give us insight into the diversity of cosmic evolution. These distant, faint stars, barely visible even in the most powerful telescopes, hold the keys to understanding billions of years of history, not just for the Milky Way but for galaxies across the universe. By comparing them side by side, astronomers are not just mapping the edges of galaxies, they are mapping the edges of time itself. The future of halo star research is poised to enter a golden age, thanks to the next generation of telescopes and astronomical surveys that promise to revolutionize our ability to detect, analyze, and interpret these ancient stellar relics. Halo stars, as we've explored in depth, are more than just individual points of light. They are keys to unlocking the earliest chapters of galactic history and the evolution of the cosmos itself. But despite decades of research, our picture of the Milky Way's halo is still incomplete, especially when it comes to its faintest, most distant members and the extremely subtle details of their chemical makeup and motions. This is where the new wave of observational tools will step in, bringing unprecedented sensitivity, resolution, and data handling power to the study of halo stars. Among the most anticipated missions is the Nancy Grace Roman Space Telescope, often referred to simply as the Roman Space Telescope or RST, which NASA plans to launch in the mid-2020s. Roman will carry a powerful 2.4-meter mirror, similar in size to Hubble's, but paired with an extraordinarily wide field of view, about 100 times larger than Hubble's. This combination means it will be able to capture massive swaths of the sky in exquisite detail, making it ideal for mapping large-scale structures like the stellar halo. For halo star research, Roman's wide-field capabilities are critical because the halo is spread out over the entire sky, with its stars widely dispersed and relatively sparse compared to the crowded galactic disk. Roman will help us identify faint halo stars in regions of the sky that have not been surveyed deeply before, and because of its infrared sensitivity, it will be able to peer through dustier regions near the galactic plane where halo and disk overlap. But Roman is only one part of the upcoming observational arsenal. The Vera C. Rubin Observatory in Chile, With its legacy survey of space and time, LSSD is another game-changer. LSSD will repeatedly scan the entire visible sky over a 10-year period, producing a time-lapse movie of the universe in unprecedented detail. For halo stars, this means we will not only be able to identify them based on their faintness and color but also track their proper motions with incredible accuracy. By combining LSSD data with Gaia's already exquisite motion catalog, astronomers will extend our knowledge of halo dynamics far beyond current limits. For example, we will be able to identify faint stellar streams, the remnants of ancient galaxies and clusters torn apart by the Milky Way's gravity, that are currently invisible. These streams often contain halo stars that carry chemical and orbital signatures revealing their origins, and LSSD could uncover thousands of such streams, helping map the halo's assembly history in remarkable detail. Speaking of Gaia, while it has already revolutionized our understanding of the Milky Way by providing precise distances and motions for over 1 billion stars, its data releases are ongoing and will become even more refined. The final Gaia catalogs will include longer observation baselines, meaning even more accurate proper motions for the most distant halo stars. Gaia's reach for parallax measurements, the technique for determining stellar distances, has limitations for extremely remote halo stars, but when combined with photometric distances from other telescopes like Roman and LSSD, astronomers will gain a more complete 3D map of the halo than ever before. On the spectroscopic front, new instruments are coming online to measure the chemical compositions of halo stars with a precision that was previously unattainable. The foremost 4-meter multi-object spectroscopic telescope on the Vista telescope in Chile will soon conduct massive surveys, obtaining spectra for millions of stars. This will allow us to chemically fingerprint huge numbers of halo stars, identifying which ones share common origins. By spotting stars with identical or very similar abundance patterns, astronomers can reconstruct ancient stellar families and link them to specific merger events in the galaxy's past. Similar surveys, like we've on the William Herschel Telescope and DESI, Dark Energy Spectroscopic Instrument, will further expand our chemical and kinematic census of the halo. Even more ambitious are the future extremely large telescopes, the Giant Magellan Telescope, GMT, the 30-meter telescope, TMT, and the European Extremely Large Telescope, ELT. These ground-based behemoths, with mirrors 25 to 39 meters across, will collect immense amounts of light, enabling the study of individual halo stars at distances that are currently beyond reach. With their massive light-gathering power and adaptive optics systems, these telescopes will not only resolve faint stars in the outer halo but also dissect their spectra in exquisite detail. This means detecting even trace amounts of rare elements, which can tell us about specific types of ancient supernovae and the chemical environment in which the stars formed. On the computational side, the coming decade will also see enormous strides. The flood of data from Roman, Rubin, Gaia, and spectroscopic surveys will require sophisticated machine learning and artificial intelligence algorithms to sift through billions of data points, flagging potential halo stars and identifying patterns that might otherwise be missed. Simulations of galaxy formation, already incredibly detailed, will be run at even higher resolutions on next-generation supercomputers, allowing theorists to predict exactly what kinds of halo substructures we should see, and then match those predictions to real observations. The impact of all these tools working together cannot be overstated. The Milky Way's halo will no longer be a faint, sparsely sampled structure with large gaps in our knowledge. Instead, it will become a richly detailed map of stellar motions, chemical properties, and substructures. We will be able to directly trace the merger history of the galaxy, identifying which stars were born here and which came from long-destroyed dwarf galaxies. We will likely discover entirely new stellar populations, perhaps stars with even lower metallicity than any currently known, which would take us one step closer to finding direct descendants of the first stars after the Big Bang. Moreover, studying halo stars in unprecedented detail will have ripple effects across many areas of astrophysics. Their motions will refine our understanding of the Milky Way's dark matter halo, which in turn will help constrain the properties of dark matter itself. Their chemical compositions will shed light on the earliest nucleosynthesis events in the universe, telling us how and when the first heavy elements were forged. And by comparing our halo to those of other galaxies, we'll gain a better sense of whether the Milky Way's formation history is typical or unusual. The next few decades could even bring the first detections of intergalactic halo stars, stars that were ejected from galaxies entirely and now drift between them. With telescopes like Roman and the ELT, astronomers will have the sensitivity to find such lonely wanderers, if they exist in detectable numbers. These would be the ultimate tracers of galaxy interactions and gravitational slingshot effects, and could even offer insights into events that happened billions of years ago in completely different regions of the local group. In short, the future of halo star research is about to be transformed by a perfect storm of technological advances: wide-field imaging, high-precision astrometry, massive spectroscopic surveys, giant telescopes, and sophisticated computational tools. The result will be not just a clearer picture of our galaxy's outskirts, but a deeper understanding of the processes that shaped the universe in its earliest epochs. If the past few decades of research were about discovering that the halo exists and beginning to chart its basic outlines, the coming era will be about exploring it in full, intricate detail, turning what was once a faint, mysterious glow into a vivid and complete story of cosmic evolution. There is something deeply humbling about looking up at the night sky and realizing that some of the faint, ancient suns scattered far above have been burning for more than twice the age of our planet. Halo stars, these aged, wandering beacons from the dawn of time, began their nuclear fires long before the Earth was even a thought in the universe's unfolding story. They lit up before the sun existed, before the planets spun into being, before any oceans or forests or cities could ever reflect their light. They are not simply old stars. They are cosmic witnesses, archivists of epochs so far removed from our everyday human scale that they make even the oldest civilizations on Earth seem like brief sparks in the dark. To stand beneath their light, or even to study their properties from a distant laboratory, is to engage with a fragment of history so ancient that it brushes against the very origins of everything. When we talk about the age of halo stars, it's easy to slip into numbers. 12 billion years, maybe more. But numbers, however impressive, fail to convey the sheer immensity of that time. 12 billion years ago, the universe was young, barely out of its infancy. The first galaxies were just starting to take shape. The heavy elements that make up the human body, carbon, oxygen, iron, barely existed, forged only in the hearts of the very first stars and distributed in the faintest traces. Yet these halo stars took form, igniting with just enough hydrogen and helium to burn slowly, steadily, across eons. Their light began traveling through space so long ago that, if one could trace its journey in reverse, it would lead not merely to a different age, but to a universe with a completely different structure, dimmer, smaller, and utterly alien. And there's a certain philosophical strangeness in knowing that while humanity has been around for perhaps 300,000 years, these stars have already existed for 40 times that span. Every rise and fall of human culture, every war, every discovery, every piece of art, has unfolded while they have quietly continued their fusion fires, either hurried nor disturbed. They have endured glacial epochs, shifting continents, mass extinctions, and the birth of entire civilizations without the slightest change in their fundamental nature. Their presence is a quiet rebuttal to our sense of urgency. They remind us that not all clocks tick at human speed. These stars also force us to confront our position in time. In a way, humans tend to think of the present as the real moment in history, as if the universe has been working toward this point all along. But halo stars tell a different story. They show us that the cosmos was vibrant and dynamic long before we arrived, and will continue to be so long after we are gone. In their lifetimes, the Milky Way has transformed dramatically, spiral arms have shifted, companion galaxies have collided and merged, and dark matter halos have expanded and reshaped the galactic architecture. The universe they were born into is not the same as the one they inhabit now, yet they persist, constant in their own quiet way, even as everything else changes. From a more personal perspective, there's something both comforting and unsettling about this kind of endurance. Comforting, because it tells us that the universe has a kind of stability, a continuity that can outlast every turbulence we experience. Unsettling, because it forces us to recognize how fleeting we are. Compared to a halo star, an entire human lifespan is less than a breath. Even the collective existence of our species is but a flicker. Yet perhaps there is beauty in that contrast. We are ephemeral observers of something eternal. Our brevity does not diminish the significance of our experience. If anything, it makes the act of witnessing these ancient lights even more precious. This perspective also reshapes the way we think about change. On Earth, we measure history in decades, centuries, maybe millennia. We see progress and decline, rise and collapse, in rapid succession. But halo stars live in a realm where change is glacially slow, where a billion years is a manageable unit of time. For them, the spiral arms of the Milky Way are not static backdrops but slow rivers of stars, shifting position over hundreds of millions of years. For them, galactic collisions are not sudden catastrophes but long, drawn-out dances of gravitational attraction. Our definition of fast barely registers on their timescales. When we measure ourselves against such patience, we see that our frantic pace is not the universe's natural rhythm, it is ours alone. There's also an element of existential awe in realizing that halo stars have seen the universe evolve through some of its most pivotal chapters. While they cannot literally perceive in the way we do, they have been present for the cooling of the cosmic background radiation, for the birth of countless new generations of stars, for the slow assembly of large-scale cosmic structures. In a poetic sense, they are the silent witnesses of cosmic history. If they could speak, their stories would not be of years or centuries, but of eons, the gentle deepening of the night as the first galaxies gathered, the gradual enrichment of the interstellar medium with heavier elements, the quiet but relentless expansion of space. The philosophical weight deepens when we consider that these stars were here before Earth and will remain long after it. Many of them will still be shining when the sun has swollen into a red giant and shed its outer layers, leaving behind a white dwarf. They will be here when the Milky Way merges with Andromeda, forming a new galaxy with a different structure entirely. They may even persist into the far future when the stars of the disk have burned out and the universe is entering its degenerate era. The endurance of these stars turns them into a kind of bridge across cosmic time, connecting the earliest eras to the distant future in a single continuous thread of light. Studying them, then, is not only a scientific exercise but also a philosophical one. They are a reminder that time is vast, that our own perspective is necessarily narrow, and that there is value in looking beyond the immediate moment. We live in an age where attention is fragmented and focused on the near term, but halo stars encourage us to expand our view, to see our existence as one moment in a grand, ongoing story that has been unfolding for billions of years. They remind us that the universe is not a static backdrop for human affairs, but an ever-changing, unimaginably large system in which we are newcomers. In this way, halo stars are both cosmic artifacts and cosmic teachers. Their light carries physical data, chemical signatures, velocities, distances, but it also carries a lesson about humility and scale. They tell us that the universe does not revolve around us, that we are part of something older and greater than we can fully grasp. And paradoxically, this realization can be liberating. If our entire civilization is just a small note in the symphony of cosmic history, then our mistakes, while important to us, lose their crushing weight on the grand scale. Our triumphs, too, become part of something larger, a shared cosmic heritage that includes not only life on Earth but every star, every galaxy, every molecule that has ever existed. Ultimately, the philosophical perspective offered by halo stars is one of connection. We are made of the same hydrogen and helium that fueled their births, and of the heavier elements forged in even older stars before them. The atoms in our bodies were once part of the same universal material that swirled into these ancient suns. We are not separate from them, we are kin. When we look up at the halo and see one of those faint points of light, we are not just looking back in time, we are looking at family. Family that has endured across almost the entire history of the universe. Family that will continue long after we are gone. And there is something profoundly beautiful about that. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.